Hello friends, it's a beautiful morning here in Kigali. I hope everyone is doing great. IBM is here to give you another episode of Learning Physics, and today I plan to talk about a different unit which is going to be deformation. Remember, we are solving AS past paper questions, and this is going to be specifically deformation of solids. So we're going to solve past paper questions in deformation of solids, and this is going to be part one of these videos for deformation of solids. In the unit of deformation of solids, which your teacher must have taught in class, I know you remember mostly Hooke's law in this unit. You must be remembering stress, strain, and Young's modulus, and those are the same concepts we are going to talk about. We are going to talk about Hooke's law. We shall talk about elastic and plastic deformation, stress, strain in Young modulus, elastic potential energy, and so many more. So the questions will rotate around Hooke's law. They will rotate around elastic and plastic deformation, stress, strain, and Young modulus, elastic potential energy, and so much more. Sometimes there will be overlap of questions from different topics, but I know we shall be able to blend the information and understand the concepts. So without wasting any much time, I want us to go to the document of past paper questions. So this is the document. Remember, the document is attached in every video description. You just copy the link, paste in your browser, the document will open and ready for download. Download, you can print per topic. This is the document, paper 2 past paper questions. And today we are going to be looking at, I want us to look at deformation of solids, which is, I think we have finished physical quantities and units. We have finished waves, we have finished particle physics, we have finished dynamics. Now we are on deformation of solids. So deformation of solids is on page 230 and 21. So I'll search 221 to, it is 321. So deformation is on page 321. Here we are. Deformation of solids. And we are starting with the first question. The first question is asking us to define the Young modulus of a material. From your classes, the teacher must have defined Young modulus as stress divided by strain. Young modulus is the ratio of stress over strain. That is Young modulus. A metal rod is compressed as shown in the figure here. We have compressing forces. The variation with the compressive force F of the length L of the rod is shown in the figure. L is in millimeters, F is in kilonewtons. Use figure 4.2 to determine the spring constant K. So from what you studied with your teacher, you must have mentioned that the force F is equal to K times the extension, which will be changing L, Kx, or changing the length. That is the extension. So this delta L is the extension. So the graph drawn is for L over F. That means change in extension is going to be equal to F over K. On the y-axis, we have change in L. On the x-axis, we have F. So it means the gradient is going to be 1 over K. So the gradient is going to be 1 over K. That means K is actually going to be the reciprocal. So K is going to be 1 over the gradient, which is actually going to be equal to change in F. That is going to be change in F divided by change in L. If I get the reciprocal, K is going to be change in F over change in L. That is going to be the gradient. So we substitute change in F, that is from 0 to 90, which is going to be 90 minus 0. Of course, this is kilo. So that will be times 10 power 3. Then change in L. L is from 150, and I think this is 48. That is going to be 150 minus 148. Remember, this is in millimeters on the y-axis, so it will be times 10 power negative 3. So I just press my calculator. So in my calculator, I'll open the brackets, 90 exponent 3 divide by open brackets. This is 150 minus 148 exponent negative 3. What is that? Sorry, let me repeat this. 90 exponent 3 divide by open another bracket 150 minus 148, I think that is 2. So I'll just say 2 exponent negative 3. So this is giving me 4.367, 4.5 times 10 power 7. So this is 4.5 times 10 power 7 as the value there. So 4.5 times 10 power 7 is the spring constant. You can also take just a point on the line and substitute in the formula F equals to K times L. You'll be able to find the constant K. Determine the strain energy stored in the rod for F equals to 90 Kelvin. Strain energy or elastic potential energy, that is the energy stored by deformed material, stretched material, and so on and so forth. So the strain energy E is going to be equal to a half. It is a half Fx. So it will be a half. Where there is x, I'm putting change in L, which is the extension. So this is going to be a half. The force is 90,000 times the change in extension, which is from 150 to 148. So that is 2 times 10 power negative 3. So I'll check with my calculator. A half is 0.5 times 90,000, then times 2 exponent negative 3. And that is giving me 90. So the strain energy is 90 joules. The rod in B has cross-sectional area A and is made of a metal of Young Modulus E. It is now replaced by a new rod of the same original length. The new rod has cross-sectional area A over 3 and is made of a metal of Young Modulus twice E. The compression of the new rod obeys Hooke's law. On the figure, sketch the variation with F of the length L for the new rod from F equals 0 to F equals 90. So the force is going to be the same between 0 and 90. All we are going to check is the new change in length. Let's see. So from Young modulus equals to stress over strain. Stress is force over area. Divide by strain, which is extension of original length. So you get the reciprocal, it becomes original length over extension. The extension is changing L. The extension is changing L. So for the first case, the Young modulus is E, that is in part B. The force is 90, the maximum force is 90. The original length is L naught, which is 150. Let me just put here 150. The area was A, and the extension corresponding to that was, the force of 90 was actually 2 millimeters. Let's check for the second case. The Young modulus is twice E, which is equal to the maximum force is 90. The original length was the same, 150, but the cross-sectional area is A over 3, and we want to see the extension. I'm calling it E. So we just divide the two equations mathematically. If you're a good mathematician, you can just combine the two equations to find what E is, small e. So when I divide the two equations, I have 2e divided by e. This side I have 3. The 3 in the denominator goes up, so it is 3 times 90 times 150 divided by a times small e. Then divide by, but I'm going to get the reciprocal, that is a times 2 divided by 90 times 150. So 90 times 150 has cancelled, a has also cancelled. Capital E has cancelled. So I have that 2, this on the left hand side is equal to 6. There is 6 in the numerator divided by E. I just wanted you to see that the new value of extension is going to be 6 over 2, which is 3 millimeters. And 3 millimeters means from 150 minus 3, that is equal to 147. So it means the new line will stop at 147 millimeters. So I just go back to the graph. So where there is, the graph will start from the same point, but will end at 90, 147. So I'm looking for 147. From 148, I'll count 5 small squares. 1, 2, 3, 4, 5. I think that is 147. So I will just use my ruler and draw a straight line. So that will be our graph. That will be our graph. You can draw a better line with your ruler. So the line is going to be below the one which is already there, and it will be stopping at 147 at when f is 90. Okay. For the deformation of a wire under tension, define stress. I've already talked about stress. Stress is going to be simply defined as force over cross-sectional area. Force over cross-sectional area. Then strain. Strain is going to be extension over original length. So strain is extension over original length of the material. Then a wire is fixed at one end so that it hangs vertically. The wire is given an extension x by suspending a load F from its free end. The variation of F with x is shown in the figure here. So here we have a variation of F with x. The wire has cross-sectional area 9.4 times 10 power negative 8 and original length 2.5 meters. Describe how measurements can be taken to determine accurately the cross-sectional area of the wire. Since the wire has a circular cross-sectional area is going to be actually pi d squared over, pi r squared, which is pi d squared over 4. So in other words, we need to find the diameter. To find the diameter, we shall use either a micrometer screw gauge or a digital caliper. And every time we are taking diameter of a wire, we take several readings at different points or different places along the wire. We get the average of those values, and that will be the most reliable diameter. So one, we shall measure the diameter of the wire using a micrometer screw gauge. Measure the diameter of the wire using a micrometer screw gauge. Or it can be a digital caliper. A vernier caliper won't give a very a very nice value. So a digital caliper would do better. So we measure the diameter of the wire using a micrometer screw gauge, but we want to determine the value accurately. So we are going to take several readings, several measurements. Take several measurements in different places along the wire, and obtain their average. So we shall take several measurements in different places along the wire and obtain the average diameter. Now we can determine the area. Determine the area from area is equal to pi d squared over 4. So we can now determine the area from that expression now that we have an accurate diameter. Determine the Young modulus E of the material. We know that Young modulus is stress over strain. Young modulus is equal to stress divided by strain. Stress is force over area. Strain is extension of original length. So this will be L original length over extension E. So we now substitute. Force is 4, original length is 2.5. Area was given as 9.4 times 10 power negative 8. Then the extension is from 0 to 0.8, but remember it is in millimeters. So we shall say times 0.8 times 10 power negative 3. So I'll just check my calculator. 4 times 2.5. I'm going to divide this by 9.4. I'll open two brackets. One is for 9.4 exponent negative 8, close the first bracket, and then times, open another bracket, 0.8 exponent negative 3, close that second bracket, then close the whole bracket. And therefore I am getting 1.32. So this is giving me 1.32 times 10 power, that is times 10, actually 1.33 times 10 power 11, if I round off correctly, 1.33 times 10 power 11. So this is going to be 1.33 times 10 power 11 pascals. That will be the Young modulus. Use the figure to calculate the increase in the energy stored in the wire when the load is increased from 2 newtons to 4 newtons. The load is increased from 2 newtons to 4 newtons. Let's go back to the graph. From 2 newtons, the load is increased from 2 newtons to 4 newtons. So the work done is going to be the area under this part of the graph. It is the area under that part of the graph. You can take it as a trapezium. You can find the area of the larger triangle minus the area of the smaller triangle. All those will give you the same answer. So the increase in energy E is going to be equal to the area under the graph. The area under the graph. I'll just use the simplest method, which is the large triangle, which is a half times 0.8 times the height, which is 4. That is for the large triangle, that is the area, minus for the small triangle. The small triangle, the base is 0.4 and the height is 2. So I'll say minus a half times 0.4, then times 2. But remember, in the numerator, each of these is in millimeters, so this will be times 10 power negative 3 to change to meters squared. I'm changing each of these to meters on the numerator, so this is giving me, I can check with the calculator. So a half is 0.5 times 0.8 times 4. Then minus again 0.5 times 0.4, then times 2. That is 6 over that is 6 over 5, which is 1.2, but there is a power of 10 here, so it is 1.2 times 10 power negative 3, because there was a power of 10 somewhere there. Alternatively, you could have taken it as a trapezium, another method using a trapezium. Area of a trapezium is a half into b, a plus b. Let's look for a. A will be this height, this distance here, that is a, which is 2, and b will be the other one, which is 4. So I will say 2 plus 4. Then times the h. The height is going to be now between 0.5 and 0.8, which is 0.4. So plus the h, which h is 0.4, but remember it is times 10 power negative 3. So we can still verify this. So 2 plus 4, that is of course 6. So we have a half, which is 0.5 times 6 times 0.4 exponent negative 3, which is still 1.2 times 10 power negative 3 joules. The wire in B is replaced by a new wire of the same material. The new wire has twice the original length, has twice the length, and twice the diameter of the old wire. So length is twice, diameter is twice. The new wire also obeys Hooke's law. On the figure, sketch the variation with extension x of the load F for the new wire from x equals 0 to x equals 0.8. So total extension is going to remain the same. Let's just recall Young modulus is equal to F, original length, over area times extension. The wire is replaced, they have the same material, so Young modulus is the same for the same material, so E is the same. So I'll say for the first wire, Young modulus is E. The force, the maximum force is 4 from the graph, you can check. The maximum force is 4 from the graph. The maximum force is 4 from the graph. Let the original length be L naught. The cross-sectional area, let it be A. And the extension, the maximum extension is 0.8. I'll take it 0.8 maximum extension. Remember, area is pi d squared over 4. Area is going to be pi d squared over 4. So this is going to be equal to 4 L naught over pi d squared. The 4 goes up, so pi d squared times 0.8, then times 4 upwards. So for the first one, we have that the Young modulus is going to be equal to 16 L naught over pi d squared times 0.8. That is for the first one. Then for the second one, the Young modulus is still the same. Where shall I write? Okay. E is still the same, but the diameter L naught is twice. So I'm going just to change L naught and diameter. So the other one will be 16 into twice L naught because the length of the new wire is twice, divide by pi, and the diameter of the new wire is twice, so this will be twice d squared. Again, we want the total extension to be 0.8, so I'm just now going to combine those two equations. I will come here for the first one. The first one, the Young modulus, was equal to 16 L naught over pi d squared times 0.8. For the second one, E is equal to 16, where there is L naught, I put there twice L naught, over pi, where there is D, I put there twice D squared times 0.8. So when you equate the two equations, we are just trying to see where the force is, the maximum force. We just want to find sorry, for the second wire, the force is not 4. Here the force is not 4, it is going to be F times 4. So I will just replace this with F times 4. So this will be F times 4. The 4 which is for the diameter is up there. So for the second one, it is F times 4. Sorry about that. Okay, so we equate the two equations. So we have 4 times F. When we equate the two equations, you notice that pi has cancelled, 0.8 has cancelled, this L has cancelled with that one. The d squared, remember, okay, we shall have 16 over d squared is equal to, here you have 4 times 2, which is 8. That is 8. In the denominator, you have 4d, but is squared. That means, 2d, which is squared, which is 4d squared. So d squared has also cancelled. There is an F. Where is the F? F is here. F is there. By 4, 1, by 4, 2. I wanted you to see that F is going to be 16 newtons. So when the diameter is doubled and the length is doubled, we see that the force is 16 newtons. The maximum force corresponds to 0.8 millimeters is 16 newtons. Therefore, my graph at 0.8 will go up to 8. Sorry, this is not 16, it is 8. Because by 4, that is 2. You have 16 on the left hand side and you have 2 on the right hand side. So that is 8. So this is 8 newtons. So the graph goes up to 8 newtons. So I'll draw a new graph which goes up to the corner. Let me increase the weight. So that will be your graph. The analysis is what is very important here. You can write two equations. The first one using the first conditions. And I try to write the second equation using the second conditions to try and find what is not known. A spring is attached to one end, to a fixed point and hangs vertically with a cube attached to the other end. The cube is initially held so that the spring has 0 extension. Okay, so they have given us the dimensions of the cube, the density of the water. Then here, when it is submerged, the base is at a distance 7.0 centimeters below the water level. The cube's weight is 4 newtons and sides are 5.1 centimeters. The cube is released and sinks into the water as the spring extends. The cube reaches equilibrium with its base at a depth of 7 centimeters below the water surface as shown. The density of the water is 1000 kilograms per meters cubed. Calculate the difference in the pressure exerted by the water on the bottom face and on the top face of the cube. So what is the difference in pressure? pressure at the top of the cube, if the height on the top is H1 and the height to the bottom is H2, pressure at the top is going to be H1 density times G. That is pressure on top. Pressure at the bottom is going to be H2 density times G. Then the difference in pressure is going to be the difference between those two, which will be density times G into H2 minus H1. But I want you to see that H2, that is the height of the top to the bottom, minus the height of the water level to the top of the cube is the same as 7.0, which is the difference in H, which I'll just call delta H. Therefore, the change in pressure between the top and the bottom is going to be density times G times change in H, which is going to be density is 1000, G is 9.81, then change in H is just going to be the 7 centimeters. Actually, it is not 7 centimeters, it is going to be just the height of this box, because H2 is from the water level on top to the base of the cube. H1 is from the water level to the top of the cube. To get difference between H2 and minus H1, you just get it is going to be actually the height of this water cube, this cube. Therefore, this is going to be times 5.1 times 10 power negative 2, because it is in centimeters. It will not be 7 centimeters, not at all. So this is going to give us, from our calculator, 1000 times 9.81 times 5.1 exponent negative 2, and that is 500.3. Use your answer in A to show that the upthrust on the cube is 1.3 newtons. Remember, upthrust is due to the difference in pressure, and if this was equated, I want to just remind, if this was equated to force over area, you notice that the force on the top, F1 will be area H1 density times G. The force at the bottom will also be area H2 density times G. The difference in the two forces will be F2 minus F1, which is the upthrust, would be equal to the area times the difference in the two values, H2 rho 2, it is the same as the change in pressure. So that is area times change in pressure. So the upthrust force, I'll quote F upthrust, is going to be equal to the area times, or the pressure times the change in area, which is equal to the pressure, difference in pressure. Actually, the area is not changing, it is the difference in pressure times the change in area. So I will say difference in pressure. It will be difference in pressure times the area, which is going to be equal to, the area is given as, because it is a cube, the area is going to be 5.1 times 5.1, but remember it is in centimeters. So the change in pressure is 500.31 times the area, which is 5.1 times 10 power negative 2, again times 5.1 times 10 power negative 2. That is area, because it is a cube, sides are equal. So I check my calculator, 5,500.31 times 5.1 exponent negative 2 times 5.1 exponent negative 2. And this is giving me a 1.30, which is approximately 1.3 newtons as required. Then calculate the force exerted on the spring by the cube when it is in equilibrium. We go back to the cube. We want the force exerted on the spring by the cube. First of all, the weight of the cube is acting downwards, so we have weight downwards. And when it is immersed in the liquid, let me use the second diagram here. The weight is downwards. The force on the cube due to the liquid upwards. This is the force due to the upthrust. Then there should be tension in the spring, which I'm calling T. So when I combine the tension in the spring plus the upthrust force, it should be equal to the weight downwards if the cube is in equilibrium. And therefore we want the tension T. So the force due to the upthrust plus the tension in the spring, which is the force exerted on the spring by the cube, plus the tension must be equal to the weight. So it means the force we want, force on the spring, is now going to be the weight, which we know as 4.0, minus the force to the upthrust, which is 1.3. And this is giving us, of course, 2.7. I hope I've explained this one clearly. When the cube is immersed in the liquid, the weight is downwards, the upthrust is upwards, there's a tension in the spring upwards. The upthrust force plus the tension upwards should be equal to the weight when there is equilibrium. And the tension is the one we want to find, that is the force exerted on the spring by the cube when it is in equilibrium. The spring obeys Hooke's law and has spring constant 30 newtons per meter. Determine the initial height above the water surface of the base of the cube before it is released. If it obeys Hooke's law, then F is equal to K times extension. So the extension is going to be the force, which is going to be the resultant force, that is 2.7, divided by the constant, which is 30. And I think there is a relationship here. 2.7 divided by 30. I think that is 0.09. That will be the extension. But we want the height above the surface. 0.09, by the way, this is in meters, it is not in centimeters. So this is in meters, which is approximately 9 centimeters. So for that, the extension is 9 centimeters for a restoring force of 2.7. The spring has extended by 9 centimeters. And the question is, determine the initial height above the water surface of the base of the cube before it is released. Note that when it is released, it's at a height of 7 centimeters. So, but before it is released, we are seeing the extension caused as 9 centimeters. So the height above the water surface of the base of the cube before it is released, it is going to be 9 centimeters minus 7 centimeters, which is giving us 2 centimeters. Okay, so the height above the surface is 2 centimeters. Part E, determine the cube in the water is released from the spring. Determine the initial acceleration of the cube. So we want to find the acceleration. Of course, we know that the resultant force F must be the resultant force. It is given by mass times acceleration by Newton's second law. And of course, from what we have already been given, we have that the mass M is going to be the weight divided by G. The weight divided by G, the weight was given as 4.0 and G is 9.81. So it means the acceleration is going to be the resultant force, which is the weight. The resultant force, which is given as 2.7. So that is 2.7. That is the resultant force. Divide by the mass. So divide by the mass, which is 4.0 divided by 9.81. That is the acceleration. So I'll check with my calculator. 2.7 divided by open brackets 4.0 divided by 9.81. So that gives us 6.6. So the answer here is going to be 6.6 to two significant figures. Describe and explain the variation, if any, of the acceleration of the cube as it sinks in the water. It is sinking in the water. Of course, we know that the upthrust force increases with depth because the pressure in the liquid increases with depth. Since the upthrust depends on the force at the bottom minus the force at the top, yet the force at the bottom depends on the pressure at the bottom minus the pressure at the top. The pressure at the bottom increases, the force at the bottom increases. That means the upthrust force is increasing, but note that the resultant force from up here, the resultant force or the force on the spring is equal to the weight minus the upthrust force. If the upthrust force is increasing, it means the tension is decreasing. And if the tension is decreasing, it means there is going to be a point where the tension is equal to the weight. At that point where the tension equals to the weight, it means the resultant force or the tension in the spring is going to be 0. Therefore, the acceleration is going to become 0 since there will be no resultant. So we shall simply say that the viscous force increases. Viscous force or viscous drag increases. As the object sinks, the upthrust increases or the viscous force increases. And then it is going to become constant when the weight equals to the upthrust. Note that viscous could also be friction. When the cube is not sinking, then the viscous force is 0. But as the cube moves downwards, the upthrust is increasing, the viscous force is also increasing. So the viscous force increases and it becomes constant when the weight and the upthrust become equal. So the acceleration at this time decreases to 0. The acceleration decreases to 0. So the object is sinking, there is a weight downwards. If it is not moving, there is an upthrust which is depending on its depth. So there is upthrust force. And as the object moves downwards, of course, the force at the bottom of it increases. Even the force at the top increases because the whole object is moving downwards. But then there is a force which opposes it from moving downwards or from sinking. That is what we are calling the viscous drag. So if the weight downwards is equal to the upthrust upwards, then it means the resultant force is going to be 0. Therefore, the friction force will remain constant, or the resistive force is going to remain constant. The viscous force is going to become constant. And at this point, the weight is going to be equal to the upthrust. Because remember, the viscous force depends on the speed. As the object moves downwards, its speed increases, the viscous force or the friction, or you want to call the liquid resistance or water resistance if it is in water. The water resistance increases as the speed increases, but doesn't increase indefinitely. When the weight equals to the upthrust, the speed can't increase any further. The acceleration becomes, or deceleration becomes, the acceleration becomes zero. So the speed remains constant, and therefore the viscous force also stops increasing. It remains constant. A spring is supported so that it hangs vertically as shown in the figure here. Different masses are attached to the lower end of the spring. The extension x of the spring is measured for each mass m. The variation with x of m is shown here. State and explain whether the spring obeys Hooke's law. We see a straight line somewhere, but the straight part of the line does not go through the origin, which means the extension is not directly proportional to the force. Therefore, Hooke's law is not obeyed. So the force is not directly proportional to extension. The force is not directly proportional to the extension, since the straight line does not go through the origin. So the straight part of the line does not extend to the origin, so the force is not directly proportional to the extension. State the form of energy stored in the spring due to the addition of the masses. Of course, addition of the masses stretch the spring, and that energy is called the strain energy or the elastic potential energy. Elastic potential energy, or it is called strain energy. The energy stored in the spring or the energy stored in a stretched material is called the elastic potential energy or the strain energy. Describe how to determine whether the extension of the spring is elastic. How do we determine that a material is extended elastically? We just remove the masses and see if the material goes back to its original length. If it goes back to its original length, we say that the extension was elastic. If it does not go back to its original length, we conclude that the extension was plastic. So there are two words here, elastic and plastic. Elastic and plastic. For elastic, the material goes back to its original length when the deforming force is removed. For plastic, the material does not go back to its original length. So we say remove the masses. Remove masses and check if the spring returns to its original length. Remove masses and check if the spring returns to its original length. If it doesn't, then it was plastic deformation. Calculate the work done on the spring as it extended from x equals to 40 to x equals to 160. Let's check on the graph. X equals to 40 to x equals to 160. So the work done is going to be the area under that graph. So work done is equal to the area under the graph. It should always be the area with the x-axis, with the extension axis, or the axis of length, or change in length. So it is area under the graph. And the area under the graph is going to be a half times, you can consider this as a trapezium, where this part is A and A is going to be, I think the scale here is 50 divided by 10, which is 5. So this is 55, 60, 65, that is 70, that is A. And the B is going to be, I think this is 145. So A is 70, B is 145, and the H is 160 minus 40, which is 120. So we are taking it as a trapezium, so that would be A, which is maybe 155, 45, plus B, which is 70. But remember, on the vertical it was in grams, yet we want answer in joules. So we change this to kilograms times 10 power negative 3. That is changing the masses to kilograms. Then multiply by x-axis. Oh, by the way, these were masses. The force is supposed to be m times g. On the vertical, it is supposed to be force, which is m times g. So I'll multiply this by 9.81, then times the x-axis is 120 in millimeters, so it's 120 times 10 power negative 3. You could also have used a half f x, but remember f is going to be mg, so that is a half times mg, then times the extension x. So this part here is equal to a half f, which is a half mg. And I now press my calculator. Note why I multiply by 10 power negative 3, because the mass was in grams. Note why I multiply by 9.81. This is area under the graph, but on the vertical axis we are supposed to consider force, which in this case will be the weight that is given by m times g. So I press my calculator. So in my calculator I have 0.5, that is a half, times, I'll open the brackets, 145 plus 70, then times and exponent negative 3. Let me repeat this. I'll say 145 plus 70 times 0.5 exponent negative 3 times 9.81 times 120 exponent negative 3. And I'm getting a 0.126. So this is approximately 0.313. So the work done is approximately 0.13. The Young modulus of the material of wire can be determined using the apparatus shown here. You must have done this experiment in your class. So we have a mark. There should be a mark put on. There should be a mark put on the wire, because you are going to measure the extension. Then the load, we are going to add masses here to find the force. One end of the wire is clamped at C, and a marker is attached to the wire above a scale S. A force to extend the wire is applied by attaching masses to the other end of the wire. The reading X of the marker on the scale S is determined for different forces F. Then the variation with X of F is shown here. So this is F with X. Then the length of the wire from C to the marker for F equals to 0 is 3.50 meters. That is going to be the original length when F is 0. The diameter of the wire is 0.38 millimeters. That means, remember, the area is equal to pi r squared, which is going to be pi d squared over 4. Diameter is radius divided by 2. Use the gradient of the line to determine the Young modulus E. So we know that Young modulus E is equal to stress divided by strain. Stress is force over cross-sectional area, and strain is extension of original length. So this becomes original length over extension. And we have a graph of F against extension. That means change in F over change in extension is going to be the gradient. So this is going to be gradient multiplied by L naught over A. So we want to find Young modulus E. So I'm just going to substitute in this gradient. I'm getting the gradient of this line. So this will be 40 minus, I think this is 5 on the vertical, and this is, I think this is 3.2, and I think this is 11.6. The scale on the x-axis is 2 divided by 10, which is 0.2 on the x-axis. So I'm finding the gradient is going to be 40 minus 5 divided by, on the x-axis, it is 11.6 minus 3.2. And this is going to be times 10 power negative 3, because this was given in millimeters. But remember, the gradient must be multiplied by L naught. L naught is 3.5 divided by the extension. No, divide by the area. And area is pi d squared over 4. Since we have the diameter, to simplify life, let me just use the radius instead of the diameter. The radius is going to be 0.19. So I'll just say pi r squared. So this will be pi times r, which is 0.19, but it is in millimeters, so it will be times 10 power negative 3, and this will be squared. Okay, let's check the calculator. So I'll just do, I can do numerators first, then I divide. So I have 40 minus 5 times 3.5. I'm going to divide by the first bracket. So divide by, open brackets. Okay, I'll open two brackets because dividing when the power is outside is going to be hard. So divide by 11.6 minus 3.4.2, close the brackets, times 1 exponent negative 3. So that's what I have. Again, I divide by, there is pi. There is pi into brackets 0.19 exponent negative 3, but this is squared. Close the second bracket. So I am getting Young modulus as 1.286 or 1.29. 1.29 times 10 power 11. So Young modulus E is 1.29 times 10 power 11 pascals. And we want the answer in terapascals. So we are going to divide this by tera. 1.29 times 10 power 11 divided by 10 power 12. So the answer, I'm dividing it by 1 exponent power 12. 1 exponent 12. And this is 0.129. 0.129 or approximately 0.13 terapascals. The experiment is repeated with a thicker wire of the same length, same material, same length. So same material means the same value of Young modulus, same length. State how the range of the force F must be changed to obtain the same range of scale readings as shown in the figure. So it is a thicker wire, that means it has a larger cross-sectional area. So if we want to have the same range of scale readings, it is a thicker wire. The Young modulus is the same. Look at the formula. E is equal to F L naught over A times E. The Young modulus is the same. The length is the same. We want to have the same scale reading. That means the extensions should be the same. But the area has changed. We see that force is directly proportional to the area. Thicker wire means a larger cross-sectional area. A larger cross-sectional area will need also a larger range of forces. So it means a larger range of F is required. That is, this should be actually greater than they should be greater than this here. This was 40, so they should be greater than actually 30, around 40 or greater than 37. So to cause the same, we shall need a larger range of F. A large range of F is required. A large range of F is required. Here we had a range of around 40 minus 5, that is 35. So we need a large range of F. This could be maybe greater than 35. So we need a large range of the values of F to cause the same extensions if the cross-sectional area has been increased. A metal wire has an unstretched length L and area A, and area of cross-section A. When the wire supports a load F, the wire extends by an amount delta L. The wire obeys Hooke's law. Write down expressions in terms of L, A, F, and delta L for the applied stress. We know that stress is equal to force over area. So F is given, area is given. So this will be F over A. Then the tensile strain. So we know that strain is equal to extension over original length. The extension is given as delta L, the original length is given as L. So strain is going to be changed in L over L. Then the Young modulus. The Young modulus is stress, which is F over area, divided by extension, that is L naught over E. So we divide FA by the other one. We are now dividing F over A by changing L over A, which is going to be L over change in L. So this is going to be FL divided by area times change in L. A steel wire of uniform cross-section area is heated to a temperature of 650 Kelvin. It is then clamped between two rigid supports as shown in the figure here. The wire is straight but not under tension, and the length between the supports is 0.62 meters. The wire is then allowed to cool to 300 Kelvin. When the wire is allowed to contract freely, a 1.0 meter length of the wire decreases in length by 0.012 millimeters. So for every 1 meter length, there is a decrease of 0.01 millimeters for every 1 Kelvin decrease in temperature. Show that the change in length of the wire, if it were allowed to contract as it cools from 650 to 300, would be 2.6 millimeters. So the change in temperature here is equal to 650 minus 300, which is actually 350 Kelvin. For every 1 Kelvin decrease in temperature, 1.0 meter length of wire decreases by 0.01 millimeters. So it means that 1 meter, if the temperature decreases by 350 Kelvin, the change in length, change in L for 1 meter, is going to be actually the increase. Change in L for 1 meter is going to be actually 0.012 millimeters times 350 for that change, for that temperature. Because for 1 Kelvin, the change was 0.012 millimeters for 1 meter of the wire. But now note that the total length of the wire is 0.6 meters. So the total change in length, delta L, is going to be equal to 0.012 millimeters times 350 times 0.62, and this is going to give us 0.012 times 350 times 0.62, which is giving us 2.604, which is approximately 2.6 in millimeters. So for 350 Kelvin and 0.62 meters, the change in length is going to be 0.012 millimeters times those values, which gives us 2.6 millimeters. That is the change in length. The Young modulus of steel is 2.10 times 10 power 11 pascals. Calculate the tension in the wire at 300 Kelvin, assuming that the wire obeys Hooke's law. So Young modulus E is equal to force over area, that is force over area, that is stress, then divide by strain, which is extension of original length. So this would be original length over extension. I get the reciprocal. So the Young modulus has been given as 2.0 times 10 power 11 pascals. The force is not known. The original length of the wire was 0.62. Divide by the cross-sectional area of the wire. The cross-sectional area of the wire. They gave us the cross-section area 7.9 times 10 power negative 7. 7.9 times 10 power negative 7. Then times the change in length. Assume that the wire obeys Hooke's law. Calculate the tension in the wire at 300 Kelvin. So since it has changed from 650 to 300 Kelvin, the change in length is 2.6. So this is going to be 2.6 times 10 power negative 3, since it was in millimeters. So I now press my calculator. I'm just going to make F the subject. I'm simply going to make F the subject. So F is going to be 2.0 times 10 power 11 times 7.9 times 10 power negative 7 times 2.6 times 10 power negative 3 divide by 0.62. So 2 exponent 11 times 7.9 exponent negative 7 times 2.6 exponent 3 divide by 0.62, and I see this is 6.6. Let me check this again. 2 exponent 11 times 7.9 exponent negative 7 times 2.6 exponent negative 3 divide by 0.62. Yeah, so this is 662. 662.6 or approximately 660 newtons. You must be able to press your calculator very carefully and always double check. The ultimate tensile stress of steel is 250 megapascals. What do we mean by ultimate tensile stress? The maximum stress that a material can withstand before it breaks. That is the ultimate tensile stress. Use this information and your answer in part 2 to suggest whether the wire will in practice break as it cools. Let's first check the stress that is applied. The applied stress, of course, is going to be equal to the force, which is the tension, around 660, which we have got above, divided by the cross-sectional area. I'm using stress as force over area. The area was 7.9 times 10 power negative 7. And this is 660 divided by 7.9 exponent negative 7. The ultimate, since this is given in mega, I'm going to convert this to mega. So this is divided by 1 exponent. Mega is power 6. So divide by 1 exponent 6. And I'm getting 835. So this is equal to, first of all, it was 8.35 times 10 power 8 pascals, which is 835 megapascals. So you notice that the provided stress is much greater than the ultimate tensile stress. So that means the material is most likely going to break. So we conclude by saying it will break. It will break because or since the applied stress is much greater. Let me just say greater is greater than the ultimate tensile stress. So it will break because the applied stress is greater. Am I writing greater? The applied stress is greater than the ultimate tensile stress, so the material is going to break. Okay. A spring having spring constant K hangs vertically from a fixed point from a fixed point. A load of weight L when hung from the spring causes an extension E. The elastic limit of the spring is not exceeded. State what is meant by elastic deformation. So we say elastic deformation, the material must go back to its original shape, size, or length when the deforming force is removed, or when the load is removed. So this is going to be change in shape, change in size, change in length, change in shape or change in length, and when the deforming force is removed, and when the deforming force is removed, the material returns to its original shape. It can be size, it can be length. So there's that change in length of a material, and when the deforming force is removed, the material returns back to its original length. That is what we mean by a material being elastically deformed. Then the relation between K, L, and E. So we know that force is equal to K times E. The load is L, so L is going to be K times E. So just say L is equal to K times E. Don't put there F because F is not given this expression. You have K, you have E, and L. Some identical springs, each with the spring constant K, are arranged as shown in the figure here. So these springs are in series. These ones are in parallel, these ones are both in parallel and then in series. The load on each of the spring arrangements is L. For each arrangement, complete the table by determining the total extension and the spring constant in terms of K. So let's come back here. When springs are in series, the total extension is the sum of the individual extensions. So this is E and this is E. One spring extends by E. If you put them together in series, each will extend by E, so that the total extension will be E plus E. So this is going to be twice E. And if the extension increases, it means the spring constant must actually decrease. It becomes easier to stretch this material, to stretch this. Since the load equals to K times E, the extension is now going to be twice E. The extension is now going to be twice E. If it was alone, L would be equal to K times E. Now there are two, the same load has been applied. So L is equal to K times 2E. So I'll call this one K total. So when we combine the two equations, you find that KE is equal to K total into 2E. So K total is equal to KE divided by twice E, which is K over 2. So in other words, the spring constant here is going to be K over 2, or a half K. Note that it is equivalent to taking the reciprocal of this coefficient here. When I have the total extension, I just know that the spring constant is going to be the reciprocal of the coefficient of the extension. So since the coefficient here is 2, the spring constant will be the reciprocal of 2, which is 1 over 2 times K. Let's check the second one. The second one, if the springs are in parallel, and we know that the total extension actually reduces. It reduces by a half. If one spring was to extend, if it was used alone, it extends by E. The other one is used alone, it extends by E. When you combine them, it's like the extension reduces. So the total extension is going to be 1 over 2 times E. So total extension here is going to be a half E. Think of if it was used alone, L is equal to K times E. Now they are used in parallel. The same load is applied. So the same load is going to be the new value of the spring constant times the new value of the extension, which is a half E. So it means Ke is equal to K total times a half E. So K total times E over 2 is equal to Ke. So it means E cancels. It means the total constant is twice K. So here this is going to be 2K. In other words, when springs are in parallel, total extension is just the sum of the spring constants. Here, when springs are in series, total extension is got from the reciprocals, that is 1 over total constant is equal to 1 over k plus 1 over k, which is equal to 2 over k. Then when I get the reciprocal, that will be k over 2. So even here, I just sum k plus k, we get 2k if they are in parallel. So now here we have parallel and series. Remember, when they're in parallel, the spring constant is a half e. And this one has extension a half e, and this one is e. So they are now in series. A half e is in series with e, so total becomes a half e plus e, which is equal to 3 over 2. Yes, 3 over 2e. So this is 3 over 2 times e. You can also predict that the constant is going to be the reciprocal of the coefficient 2 over 3, then times the constant k. Or you can think of L being equal to, if it was to be used one spring alone, to be k times e. Now all the three have been used. The same load is added, so the load L is equal to the new spring constant times the new extension, which is 3 over 2 times e. You equate the two equations. When you equate the two equations, you see that k total times 3 over 2e is equal to k times e, and e cancels out. So you see that k total is going to be the reciprocal 2k over 3. So the total constant here is going to be 2 over 3 times k. As simple as that. A uniform wire has length L and a constant area of cross-section A. The material of the wire has Young modulus E, resistivity ρ. A tension F in the wire causes its length to increase by delta L, so the extension is delta L. For this wire, state expressions in terms of L, A, and F, and delta L and ρ for the stress. Stress is force over area. F is there, A is there. So I'll just write F over A. Then strain. Strain is equal to extension over original length. The extension is given as delta L, and the original length is L. Then Young modulus. Young modulus is stress, which is force over area, divided by strain, which is going to be the reciprocal L over delta L. So this becomes F times L divided by area times delta L. Then the resistivity. We know that resistance is equal to rho L over A. L is there, A is there, R, rho is there, so I can write this as rho L over A. Since there is also delta L, I can also write, instead of that, I will write rho into L plus delta L divided by A as the resistivity. One end of a metal wire of length 2.6 meters and a constant area of cross section 3.8. So length is 2.6, area is 3.8 times 10 power negative 7. Is attached to a fixed point as shown in the figure here. So they have shown it to you in the figure. The Young modulus of the material of the wire is 7.0 times 10 power 10 pascals, and its resistivity, that is rho. Rho is that 2.6 times 10 power negative 80 meters, 8 ohm meters. A load of 30 newtons, so the force is 30 newtons, is attached to the lower end of the wire. Assume that the area of cross section of the wire does not change. Area does not change, is approximately the same. For this load of 30 newtons, show that the extension of the wire is 2.9 millimeters. Since they have given us Young modulus, and we have already seen that Young modulus is equal to force times L over area times cross section, times change in length. So the change in length, which is the extension now, the change in length is going to be the force times the original length divided by area times the Young modulus. Now I'm substituting. The force is the weight, 30 newtons. The original length was given as 2.6. Cross-sectional area was 3.8 times 10 power negative 7. And the Young modulus is 7.0 times 10 power 10. So we press our calculator, verify. So we have 30 times 2.6 divided by, open another bracket, 3.8 exponent negative 7. I can first divide by that and again divide by the second one, 7.0 exponent 10. So in meters, I'm getting this as 0.0029. 0.0029 meters. In millimeters, you multiply by 1,000, so that is times 1,000. And you get 2.9. Calculate the change in resistance of the wire. So we have seen that resistance is equal to rho L over A. So the change in resistance is directly proportional to the change in L. So this is going to be equal to rho times change in L over the area, since the area is not changing much. So we are substituting. The change in resistance is going to be resistivity. They gave us the resistivity as 2.6 times 10 power negative 8. Then times the change in L. The change in L, we have got it as 2.9. So that is 2.9 times 10 power negative 3 divided by the area, which is 3.8 times 10 power negative 7. So that is going to give us the change in resistance. So 2.6 exponent negative 8 times 2.9 exponent negative 3 divided by 3.8 exponent negative 7. And I have this as 1.98 times 10 power negative 4. 1.98 times 10 power negative 4 in meters, in ohms. So this is approximately 2.0 to two significant figures. It is 2.0 times 10 power negative 4 ohms. This is not in meters, it is in ohms. The resistance of the wire changes with the applied load. Comment on the suggestion that this change of resistance could be used to measure the magnitude of the load on the wire. The resistance of the wire changes with the applied load, that is with the force. And comment on the suggestion that this change of resistance could be used to measure the magnitude of the load on the wire. The magnitude of the load on the wire. Now note that this change in resistance is too small. That means this method is most likely not going to be good enough to measure the magnitude of the load on the wire, because although the change in resistance is going to be actually directly proportional to the change in L, which change in L is directly proportional to the change in load, but the change in resistance is too small. So we can say the change in resistance is very small, change in resistance is very small, so the method is not appropriate. The method is not very appropriate because the change in resistance is too small. A metal wire has spring constant K. Forces are applied to the ends of the wire to extend it within the limit of Hooke's law. Show that for an extension X, the strain energy E stored in the wire is given by that expression. Okay, so it is a metal wire, spring constant K. Forces are applied to the ends of the wire to extend it within the limit of Hooke's law. That means if a force is applied, this is going to be a straight line, force against extension X. So it means since force is directly proportional to X for Hooke's law, it means this is going to be a straight line, therefore the average force will be considered. So the energy E is going to be equal to the average force, to be the average force times the extension. And the average force, since initially the force will be 0, then maximum is F, the average force is going to be a half times F, then times the extension X. That is the average force. But then by Hooke's law, we know that extension X is directly proportional. Extension X is proportional to the applied force. Which means that F is going to be K times X. So we now combine the two equations. So E is going to be a half. Where there is F, I will put Kx, then times X, which gives us E as a half Kx squared as required. So average force and Hooke's law, that was very important for us to give us this expression here. Okay. The wire in A is now extended beyond its elastic limit. The forces causing the extension are then removed. The variation with extension X of the tension F in the wire is shown in the figure 4.1. So I want to expand this figure. So this is a graph of F against X. Energy ES is expended to cause a permanent extension of the wire. On the figure, shade the area that represents the energy ES. Of course, the energy ES which is expended is this area between the two graphs. The first part, the top graph is when it is being loaded, and the bottom part is when it is being unloaded. So it is the area below this, between the two graphs. So I will shade that area. Then use the figure to calculate the energy ES. Of course, the energy ES is going to be the area between the graphs. So I'll simply say energy is equal to the area between the graph. Now, to find that area, the easiest method is going to use the number of small squares. First of all, let's find one small square. On the x-axis, one small square is 0.2 divided by 10. This is times 10 power negative 3. because it's in millimeters. On the y-axis, one small square is 20 divided by 10, and that is in newtons. So I've changed this to meters, the other one in newtons. So this means I now have 0.2 divided by 10, that is 0.02 exponent -3. Then again times 20 divided by 10. So it means one small square is 0. It is 4 times 10 power. I hope I did this correctly. Let me check it again. On the x-axis, it is 0.2 divided by 10. That is the scale on the x-axis. So that is 0.02 times 10 power -3, then times 2, which gives us 0.04 times 10 power -3. Remember, area under the graph is energy, so this is in joules. Because it's in meters times newtons, that is joules. Therefore, it means one small square is representing that is 2 on the y-axis times 0.02 on the x-axis times 10 power -3 in joules, which is approximately 0.04 millijoules. That is one small square. So let's find the number of small squares which are full. I'll use a different color to find the number of small squares which are full. Let me use green. I'm going to try and count them. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, sorry, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. This is approximate 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 1, 2, approximate 102. So the full squares are 102. Remember, area, one small square is that. So ES for the full squares, it is going to be 102 times the representation of one small square, which is 0.04 millijoules, plus for the half squares, I will say a half times their number times that same energy. So let's see the half squares. I'll use a different color for half squares. Let me use red. The half squares are those ones which are crossed, which are not full anyway. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, or 66, 67, 68, 69, 70 if you want, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89. That is approximately 89 small squares. So that is 89 small squares times 0.04. So this is an estimate. Let me check. 102 times 0.04. 102 times 0.04. It is giving us that value plus a half is 0.5 times 89 times 0.04. So that is giving me 5.86. 5.86. It is far small. Let me check this again. Let me start with the half squares again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 1, 2, 3, 4, 5, 6, 7. Oh God. That is 107, not So this is 107. I miscounted this. Remember, this is an estimate. You cannot have exactly the same answer, but that was first more. So this is 107. So that is 107. Let me again check the full squares now. It is very hard, but patience is very important. So the full squares are those ones which are not crossed by the line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 1, 2, 3, okay, approximately 103. So I'll just add 103 here. Let me check this again. So 103 times 0.04 plus, again the others are half squares, so I multiply by half. So that is 0.5 times 107 times 0.04. Yeah, I think that is fine. So this is approximately 6.3. 6.3 millijoules. So the answer here is approximately 6.3 millijoules. It is quite hard, but patience is very important. So on this, we can add plus or minus 0.2 millijoules. Your answer will be in that range when you try to do it again. You may count more small squares or more full squares, depending on how big your graph is. Okay, suggest the change in the structure of the wire that is caused by the ES. Note that ES is the energy which is not returned. This causes permanent extension. So if there is a permanent extension, your teacher must have told that the molecules slide past each other during permanent deformation. So it means the atoms the arrangement of the atoms is going to be slightly changed. So you simply say the arrangement of the atoms or molecules is changed. When permanent deformation occurs, or when a material gets a permanent extension, the molecules stay in their new position. So the arrangement is changed. The tensile forces are applied to opposite ends of a copper rod so that the rod is stretched. The variation with the stress of the strain of the rod is shown here. So here they have showed you a variation. Let me fit it to one piece. The variation of stress to strain is shown here. Initially it is a straight line, and around here Hooke's law is no longer going to be obeyed. Use the figure to determine the Young modulus of copper. So we know that Young modulus is equal to the stress divided by strain, which in this case it can also be the gradient. I can find it from the gradient part. So I'll just use the straight line part. Somewhere here, the straight line, I will stop there, that is 2. And 2 is corresponding to 2 is corresponding to, is it 1.5? Put there my ruler. 2 is corresponding to 1. I think that's 1.8. This is 1.8 if I'm not mistaken. So this is going to be 2 times 10 power 8, of course, minus 0 over 1.8. This will be times 10 power negative 3 minus 0. So I'll have 2 exponent 8 divided by 1.8 exponent negative 3. So that is 1.1. So the Young modulus is going to be 1.1 times 10 power 11. 1.1 times 10 power 11 pascals. That is going to be the Young modulus. On the figure, sketch a line to show the variation with the stress of the strain of the rod as the stress is reduced. Of course, when the stress is reduced, the extension decreases uniformly. Therefore, this is going to be a straight line. When the stress is reduced from 2.5 pascals to 0, this is just going to be a straight line. To not fall back at the same curve, because remember the material was initially obeying Hooke's law. So for the stress, it is going to be a straight line. So that is going to be a straight line like that when the stress is reduced. So as the stress is removed, the strain varies linearly. So that would be a straight line. The walls of the tires on a car are made of a rubber compound. The variation with the stress and strain of a specimen of the rubber compound is shown here. So here they have a graph of stress against strain for rubber. You must be familiar with such a curve, such a graph. Okay, so of course the first part, this is loading, that is unloading. We are familiar with that from our lessons of dynamics. The energy which is returned is most likely the area under that between those two graphs. The area under the top curve is for loading. The area under the bottom curve is for unloading. The difference in the two areas is actually the work done, the work which is not returned during removing the deforming force. As the car moves, the walls of the tires bend and straighten. Bending and straightening. Use the figure to explain why the walls of the tires become warm. When you look at the figure, you notice that the area under the bending curve, that is loading, is greater than the area under the straightening curve, that is unloading. And if there is a difference, it means some energy is wasted as thermal energy, which warms up the tires. Therefore, we can say the area under the bending curve is greater than the area under the straightening curve. The area under bending curve is greater than the area under straightening curve. Thus, some energy is wasted as thermal energy. And of course, this is the one which is going to warm up the tires. So that is the energy which is going to warm up the tires. Alternatively, we can also explain this in terms of work done in bending the walls and the work done which in straightening the walls. The difference in the area is the work done which becomes thermal energy. So I'll write this one here. So as the car moves, the walls expand. The walls expand. As the car moves, the walls expand. Or we can say stretch. So the upper curve shows the work done in bending walls. And the lower curve shows the work done when the walls straighten. So the upper curve is showing the work done in bending the walls, and the lower curve is showing the work done when the walls straighten. And there is a difference. The difference in the area which I said is this area here between the two curves. That difference in the area, is the work done, or is the work which becomes thermal energy in the tires. So that difference is the work which becomes thermal energy in the tires, not the difference here. If I wanted the work done on loading, or on bending, I could take the area under the top curve, the total area under the top curve. If I wanted the area or the work done during unloading, I will take the area under the bottom curve. And you see that if I wanted the area, the work which becomes the thermal energy, I would take the area between the two curves. This area here between the two curves, which would be got by subtracting the area under the top curve minus the area under the bottom curve to get the energy which is wasted as thermal energy, or which warms up the tires. Okay, I've spent much on that. Hope it is clear and understandable. Define Young modulus. Now we are aware that Young modulus is stress divided by strain. The Young modulus of steel is 1.9 times 10 power 11 pascals. The Young modulus of copper is 1.2 times 10 power 11 pascals. A steel wire and a copper wire each have the same cross-sectional area, so area is the same, and length L is the same. The two wires each have extended by equal forces, so F is also the same. Use the definition of Young modulus to determine the ratio extension of copper wire over extension of steel wire. So Young modulus is stress, which is force over area, times divided by extension strain, which is extension over original length. When we get the reciprocal, it will be original length over extension. So there are two wires here. I'm making E the subject. Small e is equal to F L naught over A times Young modulus. We have a steel wire and a copper wire. So I'm going to get two equations. For steel, E for steel is going to be the force is the same, the original length is the same. They have the same cross-sectional area, but the Young modulus is not the same. I'll call it E steel. Then for copper, extension for copper, the force is the same, original length is the same, cross-sectional area is the same, but the Young modulus is not the same. I'll call it EC. Now I want the ratio of copper over steel, so I'm dividing the two equations. So E for copper over E for steel will be equal to F L naught over A EC times, I get the reciprocal because I'm dividing. A E for steel divided by F L naught. So A cancels, F cancels, L naught cancels. So the ratio is going to be E for steel over E for copper, which is 1.9 times 10 power 11 divided by 1.2 times 10 power 11. And if I just divide 1.9 divided by 1.2, that gives us 1.6. So this is 1.58, which is approximately 1.6. That is the ratio. The two wires are each extended by a force. Both wires obey Hooke's law. On figure 3.1, sketch a graph for each wire to show the variation with extension of the force. Label the lines for steel with the letter S and the line for copper with the letter C. So we have seen that extension of copper over extension of steel is equal to 1.6, meaning that the extension of copper is 1.6 times the extension of steel for the same load. So it means the extension of steel is 1.6 times the extension of steel. The extension of copper is 1.6 times the extension of steel, meaning copper extends many times than steel for the same force. Therefore, the graph of copper is going to be at the bottom. So copper extends many times. It has a larger extension for the same force. So the graph will be at the bottom. And steel will therefore be on the top. So this is going to be copper, this will be C, and the other one will be steel. So define stress. So we know stress is force over cross-sectional area. Force divided by cross-sectional area. Then strain, we know strain is extension over original length. Explain the term elastic limit. Explain the term elastic limit. So we have been talking about elastic limit, and we said when a material that when the elastic limit of a material has not been exceeded, if we remove the deforming force, the material goes back to its original length. If the elastic limit is exceeded, even when we remove the deforming force, the material does not go back to its original length. Therefore, elastic limit can be looked at as a point or the maximum load. The maximum load beyond which the material does not return to its original length or shape or size, to its original length the material does not return to its original length, or I can call it size, when the load is removed or when the deforming force is removed. So that is the elastic limit. That maximum load, if you go beyond that maximum load and you put on a material, even when you remove it, the material will not go back to its original length. In other words, the material undergoes plastic deformation. If we don't go beyond that maximum load, every time we remove the load, the material goes back to its original length. Then ultimate tensile stress. Of course, this one is the maximum stress that a material is able to support before it breaks. The maximum stress a material is able to support before it breaks. It can be defined as the maximum force. The maximum force which a wire is able to support. Maximum force which a wire is able to support before it breaks. So there's that maximum stress which a material can withstand before it breaks. That maximum force which a material or a wire can withstand or is able to support before it breaks. We can call it the ultimate tensile stress. A ductile material in the form of a wire is stretched up to its breaking point. On the figure sketch the variation with extension X and stretching force F. So because the material is ductile, a ductile material is that material which can undergo both elastic deformation, that is a straight line, and plastic deformation before it breaks. In other words, initially when the extension is very small, Hooke's law is going to be obeyed. That will be a straight line. So initially we shall have a straight line for small extensions. The material undergoes both elastic deformation, but until a point when we go beyond the proportionality limit, now it will no longer be a straight line. So now it will be a small change in force will cause a large change in extension. So initially Hooke's law is obeyed up to the limit of proportionality. Then any further change in force will cause a large change in extension. That's why you see the graph is becoming almost horizontal. Then It is not a perfect horizontal line, but I'm showing that a small change in a force is causing a large change in extension. Then the material is brittle. Of course, we know that a brittle material breaks without giving warning. It only undergoes elastic deformation and then breaks. So stretches up to the breaking point without undergoing plastic deformation. So this will be just a straight line until it breaks. A good example could be glass. You can talk about clay. So those ones they just undergo elastic deformation up to the breaking point, and they break without giving warning. Explain the features of the graphs indeed that show that the characteristics of ductile and brittle materials. So now we know from the graph, a ductile material, initially the force is directly proportional to the extension, that is for small change in force, but then later on a small change in force is going to cause a large extension. So ductile, I'll begin with the ductile material. Initially, force is proportional to extension. Force is proportional to extension. That is when we have a straight line. And later we see that a small change in force causes a large change in extension or causes a large extension. Then a small change in force causes a large extension. That's for ductile. Then for brittle, we see it is just a straight line up to the breaking point. Therefore, we say a force is proportional to extension until the material breaks. Force is proportional to extension until it breaks. Okay, so that is for the brittle material. The material just breaks without giving warning. For ductile, it will first undergo elastic deformation where normally force is proportional to extension. Then it will undergo plastic deformation where a small change in force causes a large extension until it will finally break. Okay, the force F is removed from the material in D just before the breaking point E is reached. Describe the subsequent change in extension for a ductile material. Since it has undergone plastic deformation, it will not go back to its original length. So we say does not return to its original length. It does not return to its original length. Or you would say it entered the plastic region. It entered the plastic region. The material entered the region of plastic deformation. It entered the plastic region. Or you would say the material actually gets permanent extension. So the material gets permanent extension. The material gets a permanent extension. Then how about for ductile? We saw for ductile it was just a straight line up to the breaking point. Since the breaking point was not reached, it means when the deforming force is removed, the material must be returning to its original length. So we simply say this one, it returns to its original length. Returns to its original length. It returns to its original length. Or you could say it does not retain extension. Does not retain. To retain is to continue keeping something. It doesn't retain, or it does not keep its extension. Doesn't retain extension, or there is no extension as there is no plastic region. It will not have, there will be no extension when the deforming force is removed because there is no plastic, there is no plastic region, or you would say the material is still in the elastic region. So you could say it is still the elastic region. It is still in the elastic region. So there is no extension kept. State Hooke's law. Hooke's law, your teacher must have stated Hooke's law, or you must be familiar with Hooke's law that force is equal to K times extension X. That is, extension is directly proportional extension is directly proportional to force, that is for actually small extensions. Or you can say provided the proportionality limit is not exceeded. Extension is directly proportional to force for small extensions, or you can say provided proportionality limit is not exceeded. Provided proportion So if the proportionality limit is not exceeded, then extension is directly proportional to the force. That is Hooke's law. Extension is directly proportional to force for small extensions, or provided the proportionality limit is not exceeded. The variation with extension x of the force F for spring A is shown in the figure here. So it is a graph of force against extension. We can check L is 1, 2, 3, 4. 1, 2, 3, 4. So L, this is the scale here is 2 divided by 10, 0 0.2. 6.2, 0.4, 7. This is 7.2. And here, these are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is, and that is 9.0. So the point L on the graph is the elastic limit of the spring. So we can see the graph first. Describe the meaning of elastic limit. I think we have described the meaning of elastic limit. I said the maximum load beyond which the material does not go back to its original length when the deforming force is removed, or a point beyond which the spring, since we are referring to a spring here, we can say the maximum load, or I will simply say a point beyond which point beyond which the spring does not return to its original length. When the load is removed. So the load, when the load is removed and the material has been loaded beyond the elastic limit, then it will not return to its original length. So that is the elastic limit. Okay. Calculate the spring constant K for spring A. So spring constant from force is equal to Kx. K is equal to F over X. Since it is a line going through the origin, I can just take values from the graph, but I can also find the gradient. So K is equal to the gradient, which is the change in F over the change in the extension. So the change in F, the maximum here is 7.2 to 0, and this is 9.0 to 0. So I'll just say this is 7.2 minus 0 over 9.0 minus 0, but in the denominator we shall multiply by 10 power negative 2 because the x-axis is given to 10 power negative 2. So without even pressing the calculator, you can see that 7.2 divided by 9 exponent negative 2 is actually 80. Then calculate the work done in extending the spring with a force of 6.4 newtons. 6.4 newtons, 6.4 newtons. So this is 6.2, 6.4 newtons is somewhere here. Okay, 6.4 newtons. It corresponds to, I think that is 8. So the work done is going to be the area under this part of the graph. The work done is the area under that part of the graph. So the work done in extending the material is going to be the area under the graph. And the area under the graph can be given as a half times F, then times X, or it can be a half Kx squared. Any of those can work. So I can use this a half times the force is 6.4 times X, which is between 0 to it is actually between 0 to 8 times 10 power negative 2. So that would be between 0, 8 times 10 power negative 2. Or I can use the last part of the equation, that is a half times K, which is 80, times X, which is 8 times 10 power negative 2. So when I check my calculator, a half, which is 0.5 times 6.4 times 8 exponent negative 2. So that is 0.256. 0.256 joules. So that is the work done. A second spring B of spring constant twice Ka. So the spring constant of A, remember, was 80. The spring constant of B is twice Ka, that is 2 times 80, which is actually 160. A force of 6.0 newtons extends the combination of springs. For the combination of the springs, calculate the total extension. So, of course, you can use knowledge of if you can use knowledge of combination of springs, it is fine. But of course, if this spring A extends by an extension E, which we have seen as 0.08 from the graph, extension E is 0.08 from the graph, that is in the meters, or 0.8 times 10 power negative 2 in meters. And we see that force is equal to K times extension, meaning K is inversely proportional to extension. If the spring constant of B is twice that of A, it means the extension of B is going to be a half that of A. So that will be a half times 0.08 for the same load. Therefore, this is going to be 0.04. So the total extension is going to be 0.08 plus 0.04. If A extends by 0.08 from the graph and the spring constant of B is twice that of A, it means the extension of B is actually half of that of A. But when the springs are joined in series, total extension is the sum. That's why I'm adding 0.8, that is for A, plus 0.04 for B. And that gives us 0.08 plus 0.04, which is 0.12. Then the spring constant. Since this is the total extension and we have the same load F, we can find total extension. Total spring constant K. So spring constant K is going to be equal to the load over extension. So total spring constant is the force over total extension. The force is 6.4 and total extension is 0.12. So we have 6.4 divided by 0.12 and this is 53.3. So this is 53.3. Alternatively, you can use simple ideas. You can use simple methods if you know some simpler ways of manipulating. If you know some simpler ways of manipulating constants, we know that if total extension, the other one was E plus the other one is a half E. This gives us total of 3 over 2E as total extension. And we know that spring constant is the reciprocal of the coefficient, that will be 2 over 3 times the spring constant of 1, which is going to be 2 over 3 times the spring constant of the other one, which was 80. That is going to give us 2 over 3 times 80, which gives us 53.3, the same thing. So this would be another alternative for those who know springs in details. Explain what is meant by plastic deformation. So we said a material is deformed elastically if it returns, and plastically it does not return. So plastically, when the load is removed, the material, the wire or the object does not return to its original shape, its original length or shape. When the deforming force is removed, or when the load is removed and the material does not return to its original length, then we say the material has been deformed plastically. A copper wire of uniform cross-section area 1.54 times 10 power negative 6 meters squared and length 1.75 meters has a breaking stress of 2.2 times 10 power 8 pascals. The Young modulus of copper is 1.2 times 10 power 11 pascals. Calculate the breaking force of the wire. Breaking force. So we know that stress is equal to the force over area. We want the breaking force. So the force is going to be the stress. which is 2.20 times 10 power 8 times the area, which is 1.54 times 10 power negative 6. So let's find this in the calculator. 2.2 exponent 8 times 1.4554 exponent negative 6. So that is 338.8. So this is 338.8, which is approximately 340 newtons to two significant figures. Okay, a stress of 9.0 times 10 power 7 pascals is applied to the wire. Calculate the extension. Calculate the extension. So we want the extension. So they have given us the stress is applied to the wire. Calculate the extension. So we know also that Young modulus E is equal to stress divided by strain. And remember, strain is extension over original length. So we want this is going to be stress times, of course, since strain is extension of original length, we get the reciprocal. So that will be original length over extension. So it means the extension E is going to be, I'm cross multiplying. The extension is going to be the stress times the original length divided by the Young modulus. I'm now substituting. The stress is 9.0 times 10 power 7 times the original length. What was the original length? 1.75. Divided by Young modulus, which is 2.2 times, no, 1.2 times 10 power 11 pascals. 1.20 times 10 power 11 pascals. So we shall check this in the calculator. 9.0 exponent 7 times 1.75 divided by 1.2 exponent 11. So we are seeing the extension is 1.31 times 10 power negative 3. So this is 1.31 times 10 power negative 3 millimeters. Explain why it is not appropriate to use the Young modulus to determine the extension when the braking force is applied. Why shouldn't we use the Young modulus when the braking force is applied? Of course, when the braking force is applied, it means the limit of proportionality has been exceeded. So it means the stress is no longer proportional to the extension. So we cannot determine extension when the braking force is applied. So at this point, the stress is no longer proportional. The stress will be no longer proportional to the extension when the braking force is applied. The stress is no longer proportional to the extension when the braking force is applied. Okay, a load F is suspended from a fixed point by a steel wire. The variation with extension X of F for the wire is shown here. State two quantities other than gradient of the graph in the figure that are required in order to determine Young modulus of steel. So Young modulus is equal to force over area, that is stress, divided by, I get the reciprocal, extension over, no, it is original length over extension. So the gradient is going to be F over extension, that is gradient. So we remain with the original length. So measure the original length. Measure the original length using a ruler. Then we have area. Area is going to be equal to pi r squared, which is pi d squared over 4. So we shall need a diameter, or you may need, you can find the radius or the cross-sectional area. Or the cross-sectional area. Okay. Describe how the quantities you listed in Roman 1 may be measured. Okay, this is easy. Let's see. The original length, that one is going to be measured using a meter ruler or a tape measure. Measure original length. Measure original length with a meter ruler. With a meter rule or tape measure. Or simply tape. That's number one. Number two, we have diameter. We're going to measure the diameter with a micrometer screw gauge or a digital caliper. Measure diameter with a micrometer screw gauge or a digital caliper. Of course, remember we said when we measure diameter using the micrometer screw gauge, we measure different points and we obtain an average value. Okay. A copper wire, there's this part here. A load of 3.0 newtons is applied to the wire. Use the figure to calculate the energy stored in the wire. 3.0 newtons, 3.0 newtons, 3.0 newtons. So this is going to be the area under the graph, 3.0 newtons. So energy stored is equal to the area under the graph, which can be given as a half fx, or it can be given as a half kx squared. So the energy is going to be a half times the F is 3.0 newtons times the X. The X on the X, the value of X is, I think this is 0.25, but it is in millimeters. So that is 0.25 times 10 power negative 3. So from my calculator, half is 0.5 times 3 times 0.25 exponent negative 3. And that is 3.75 times 10 power negative 4. Which is approximately 3.8 times 10 power negative 4 to two significant figures. A copper wire has the same original dimensions as the steel wire. The Young modulus for steel is 2.2 times 10 power 11, and for copper is 1.1 times 10 power 11. On the figure, sketch the variation with x of f for the copper wire for the extensions up to 0.25 millimeters. So we want extension up to 0.25 millimeters. So total extension is going to be the same. So the wire which we have there is steel, whose modulus is twice that of copper. So let's just have equations here. Young modulus E is equal to F, original length, area times E. The copper wire has the same original dimension as the steel wire, meaning L naught is the same and area is going to be the same. The Young modulus of steel is 2.2 times 10 power 11. That is, it is twice that of copper. So for steel, I have that twice E is equal to the load. From the graph, I'm going to see the load was 3 newtons. So the load is 3 newtons times L naught over area. The extension was 0.25. That is for steel. Then for copper, it is E, because for steel it is twice that of copper. Or I would say steel is E, and for copper I would say a half E, but it's the same thing. So for copper it is E. The force, we don't know the maximum force, but the original length is the same. The cross-sectional area is the same, and we want the total extension to be the same. So we divide the two equations. So I'm dividing the two equations. E over 2E is equal to F L naught A times 0.25 times, I get the reciprocal of the first equation. So that is A times 0.25 divided by 3 L naught. So E cancels F. So no, F is the one we want to find. L naught cancels, 0.5025 cancels. So you have a half equals to F over 3, which means that F is equal to 3 over 2, which is 1.5 newtons. So it means 0.25 millimeters corresponds to 1.5 newtons on the graph. Of course, 0, 0, when F is 0, X is 0. So I come back to the graph. I'm going to rub off this line here. I come back to the graph and look for 1.5. So this is 1, 2, 3, 4, 5. 1, 2.5. I think that is 1.5. 1.5 is in the center there. So I just sketch this graph. This is not good enough. It's not easy to sketch on a computer. Yeah. So what is very important is that the graph is stopping at 0.25 against 1.5 at that point there. Okay. So the mass of one end of the spring is fixed to a support A. A mass is attached to the other end of the spring. The arrangement is shown in the figure there. The mass is in equilibrium, explained by reference to the forces acting on the mass. What is meant by equilibrium? Of course, in force, density, and pressure, we shall talk about equilibrium many times. But we know that for equilibrium, the resultant force and resultant torque or resultant moment must be zero. So for equilibrium, the resultant force and resultant moment or torque must be zero. The resultant torque or resultant moment and the resultant force must be zero. So we are referring to the forces acting on this mass. The weight is acting downwards, and there is tension which is going to be acting upwards, or the force due to the spring is upwards. So we say the weight downwards must be equal to the force due to the spring, which is upwards. That is the tension. And if they are equal, then the resultant force is zero. Of course, there is no moment there. The mass is pulled down and then released. At time t equals to zero, the mass oscillates up and down. The variation with time t of the displacement of the mass d is shown here. So this is a graph of displacement against time. We know that the gradient is the speed or the velocity. And we see that the gradient is maximum when the graph is crossing the x-axis. The gradient is zero when the graph is at maximum displacement. So let's see the questions now. Use the figure to state the time, one in each case, when the mass is at maximum speed. Maximum speed, the gradient must be maximum. The graph is crossing the x-axis, that is at 0.2, 0.6, and 1.0. There we have maximum speed. So you can choose 0.2 seconds, you can choose 0.6 seconds, you can choose 1.0 seconds. So I will just say 0.6 seconds. Here, note very well that the gradient is maximum. Okay, then the elastic potential energy stored in the spring is maximum. Remember, elastic potential energy is equal to a half kx squared. So it depends on the displacement, x. Therefore, the displacement must be maximum if the elastic potential energy is maximum. So we have the displacement is maximum when x is 0. We have it when x is equal to 0.4. I mean when t is 0, when t is equal to 0.4, and when t is equal to 0.8. So we shall say 0, 0.4, 0.8 seconds. So I'll just choose one, I'll just choose 0.8. This is the one at the top, not this one. So I said it is maximum when displacement is 0. I mean when displacement x is maximum, or when the extension is maximum. And the extension is maximum when x at t equals to 0, t equals 0.4, and t equals to 0.8. Then the mass is in equilibrium. The mass is in equilibrium when the displacement is 0. And that is at 0.2. Displacement is 0 at 0.2, at 0.6, and 1.0. So the mass is at equilibrium when displacement is 0, that is at 0.2 seconds, at 0.6 seconds, and at 1.0 seconds. So I will just write here 0.6. Okay, the arrangement shown in the figure is used to determine the length L of a spring when different masses M are attached to the spring. So this is the arrangement. L is the length of the spring. Okay, so this is a graph of L against mass. L against mass. So this is at 20. Then it goes up to 35. Then this is, I think this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 0.4. So that is at this point here. However, remember this is supposed to be a graph of extension against mass, or weight or force or load, and therefore the load here, which is going to be the weight, is going to be given by m times g. Okay, and then every time we take the area with the extension axis, not with the mass or the force axis. Let's see the question now. State and explain whether the spring obeys Hooke's law. Hooke's law requires that the extension is directly proportional to the applied load. So let us see from the graph. We see it is a straight line. The original length is 20. When the load increases, we see that the extension is also increasing. So Hooke's law must be obeyed in this case. So we shall say Hooke's law requires that extension is proportional to force, not to mass. It is proportional to force. Extension is proportional to the applied force, and we see that it is a straight line. It is a straight line graph, hence obeys Hooke's law. Hence spring obeys Hooke's law. The spring obeys Hooke's law. Show that the force constant of the spring is 26 newtons per meter. Force constant, we shall just get this from Hooke's law. We know that force is equal to K times X. So the constant is going to be equal to F over X. Here we have F on the y-axis against, X on the y-axis against load. So it means K here is going to be 1 over the gradient. It is going to be 1 over the gradient. It is actually 1 over the change in X over change in F. The change in X is going to be the difference in the values of L, which is going to be the gradient. But remember, F is going to be m times g. It is going to be the weight. Since they gave us mass, F is going to be the weight, which is m times g. So we are saying that the constant K is equal to 1 over the gradient, which is going to be actually change in F over change in L, because the length is L. So the change in F, the mass is from 0.4 to 0. So I will say 0.4 minus 0. That is mass in kilograms times 9.81 to make it force or load. Then the corresponding change in length is from 20 to 35. 20 to 35. So that is 20 minus 35 minus 20, that is 15 times 10 power negative 2. So I will press my calculator. 0.4 times 9.81 divided by 15 exponent negative 2. And that gives me 26.16. So that is 26.16, which is approximately 26 newtons per meter. A mass of 0.4 kilograms is attached to the spring. Calculate the energy stored in the spring. So energy stored in the spring is simply going to be the area on the left-hand side of the line. Energy is going to be the area on, or let me say area to the left. Area to the left of the line, because the area is always with the extension axis, which can also be the same as a half k times the extension squared. So this is going to be a half times, since the mass is 0.4, we shall change it to weight or force. By the way, remember this is a half Fx. So the force is going to be a mass, which is 0.4 times g, which is 9.81, then times the extension, which is from 20 to 35, that is 15. So this will be times 15 times 10 power negative 2, and this should be, okay, that will not be squared. I'm just using a half Fx. I'm using the last one instead of this, or you can use the area. I'm just using the last part for easier calculation. So a half is 0.5 times 0.4 times 9.81. So that is it, times 15 exponent negative 2. So this is 0.294. So this is 0.294 joules. The Young modulus of the metal of wire is 0.17 terapascals. The cross-section area is 0.18 millimeters squared. You should be able to convert from millimeters squared to meters squared where necessary. The wire is extended by a force F. This causes the length of the wire to be increased by 0.095%. Calculate the stress. So we know that stress can be got from the formula since we have the Young modulus. Young modulus is stress divided by strain. And since we have the Young modulus, we have the cross-sectional area of the wire, and we have that the wire is extended by a force F. This causes the length of the wire to be increased by 0.095%. It means we now have the strain, because we know strain is equal to extension over original length. The length of the wire is increased by 0.095%. That is 0.095% times the original length. So this is going to be 0.095% of L divided by L naught. So which is simply the same as 0.095 over 100. That is for the percentage part. That is the strain. So it means the stress is going to be the Young modulus, which is 0.17 times terapascals 10 power 12 times the strain, which is 0.095 over 100. 0.17 exponent 12 times 0.095 divided by 100. So this is giving 1.68. This is 368. So it is 1.62 times 10 power 8. 1.62, I'm rounding off. 1.62 times 10 power 8 pascals. Then we want to find the force. We want to find the force. Since we know that stress is equal to force over area, it means that the force F is going to be the stress times the area. So the stress is 1.62 times 10 power 8 times the area. They gave us the area 0.18 millimeters squared. Remember, 1 millimeter or 1 meter is 1,000 millimeters. So we have to square both sides. That means the other one is going to be 1 million millimeters squared. So we get the reciprocal, it will be times 10 power negative 6. So this will be 0.18 times 10 power negative 6 to change it to meters squared. And we can check this with our calculator. 1.62 exponent 8 times 0.18 exponent negative 6. And that is 29.2 or 0.16, which is approximate 29.2 newtons. So that is going to be the force. That is going to be the force. Okay. Two wires P and Q of the same material and same original length are fixed so that they hang vertically as shown in the diagram. So we have the wires, each of the same length, the same force F is applied as shown in the diagram. The diameter of P is D and the diameter of Q is twice D. The same force F is applied to the lower end of each wire. Show your working and determine the ratio stress in P over stress in Q. Stress in P over stress in Q. First of all, we know that stress is equal to force over area. They gave us diameter. We know that area is equal to pi d squared over 4. So I'm substituting for the area here, so it becomes 4f divided by pi d squared. Now let's try to find the ratio. Let's try to find the ratio. F is the same. What is changing is d. So the ratio is going to be 4 times f divided by pi d squared. That is for p. Then I'm going to divide this one by, of course, when I'm dividing, I'll just multiply with the reciprocal of the other one. So the reciprocal, this is squared, the reciprocal of the other one, it will be pi, but remember d is squared. The other one is twice d, so it will be twice d. The other one will be twice d, and this is squared, divided by 4f. If you don't know how I'm arriving at that, let me just show you. If the first wire is this, the second wire, its stress is going to be 4f over pi. Where there is d, I'll put there twice d, but this is squared because the diameter is twice. So that is squared. Then I'm dividing these equations. The first equation divided by this equation here. This is stress for Q. And this was stress for P. So 4f cancels, pi cancels, you remain with the 4d squared divided by d squared, which gives us 4. So the ratio there is 4. Then strain. We also know that since we have are they from the same material? Let's check. If they're the same material, the Young modulus is the same. Same material, meaning E is the same. Young modulus is the same. So I'll use Young modulus. We know that strain is going to be equal to a stress over Young modulus from the definition of Young modulus. So let's find the ratio. Strain for P over strain for Q is going to be stress. It is going to be the stress of P over the Young modulus divided by the stress of Q over the Young modulus, because E is the same, which is going to be the stress for P over the Young modulus times the Young modulus over the stress for Q. So Young modulus cancels out. So this is the same as stress for P over stress for Q, which is the above expression, and that is 4. So the answer here is 4. Stress of P over stress of Q, which is 4. This is written as, I think, sigma for stress. It is not 6, it is sigma. Okay. A spring hangs vertically from a point P as shown in the figure. So we see a spring hanging vertically. A mass M is attached to the lower end of the spring. The reading X from the meter rule is taken as shown in the figure. So this is a graph of M against X. Remember, if we want force, it will be the weight, which is going to be mg on the vertical axis. Explain how the apparatus may be used to determine the load on the spring at the elastic limit. Remember, beyond the elastic limit, the material does not go back to its original length. First of all, we need to know that if the material can undergo elastic deformation by adding small masses to find small extensions. We can first add small masses or add a small mass to cause an extension. We add a small mass to cause an extension. Then we remove the mass to see if the material goes back to its original length. Then remove the mass to see if the spring returns to its original length. So we first add small masses, or we add a small mass to cause an extension, and then we remove it to see if the spring will go back to its original length. But there we have not verified, or we have not determined the elastic limit. Now, to determine the elastic limit, we repeat with larger masses. So repeat for larger masses. Repeat for larger masses and note the maximum mass for which when the load is removed, we determine the maximum mass for which when the load is removed, the spring does not return to its original length. The spring does not return to its original length. So that is going to be now the elastic limit. That mass is going to help you to determine the elastic limit or the maximum load, beyond which the material does not go back to its original length. Then state and explain whether the figure suggests that the spring obeys Hooke's law. Remember, Hooke's law requires that the force is directly proportional to extension. Let's check. This is a straight line, as of course here we have the original length. As the load increases, we see that the extension also increases. So we can say Hooke's law requires force to be proportional to extension. Hooke's law requires force to be proportional to extension, and the graph shows a straight line, hence obeys Hooke's law. The graph shows a straight line, hence the spring obeys Hooke's law. Hence the spring obeys Hooke's law. Use the figure to determine the spring constant in Newton per meter of the spring. So since it is mass against a length, spring constant is going to be force over extension x. So this is going to be the force or the change in force, the change in the load over the change in the value of x or value of the length. So the force, let me see here, it is 4 point, that is 0.42. 0.42 against, I think that is 3, and this one is 21.2 because the scale on the x-axis is 2 divided by 10, which is 0.2. So 20.2, 0.4, 0.6, 0.8, 21.2. So I will have, on the vertical axis, I have 0.42 times 9.81 because it was in mass. Divide by, on the x-axis, I have 30, 3 point, that is 30. Is it 30? Yes, 30 and 21.2. So this is 30 minus 21.2, but it was in, is it centimeters? It is in centimeters. It is in centimeters. So I will have times 10 power negative 2. Times 10 power negative 2. And I will check this on my calculator. So I have 0.42 times 9.81 divided by, we have, I will just divide by 30 minus 21.2. I will divide by the power of 10, which is 1 exponent negative 2. And that is 46.8, which is approximately 47. The variation with extension x of the force F applied to the spring is shown in the figure here. So here we have again F against x, and it is a straight line. The spring has an unstretched length, so the original length is 0.08, and is suspended vertically from a fixed point as shown here. So unstretched length is that when position x, it is in position x, it is the new length is that. So the extension here is 0.095 minus 0.080. 0.095 minus 0.080, which is 0.015. Then in this position, position y, the extension is going to be 0.12 minus 0.08, which I think it is 0.12 minus 0.08, which is 0.04. Okay, let's now look at the questions. A block is attached to the lower end of the spring. The block hangs in equilibrium at position x. When the length of the spring is 0.0 0.095. That is in equilibrium. The block is then pulled vertically downwards and held at position Y so that the length of the spring is 0.12 meters as shown in the figure. The block is then released and moves vertically upwards from position Y back towards position X. Use the figure to determine the spring constant of the spring. So we are using the graph. Spring constant K is equal to F over X, which is actually the gradient, because they gave us a graph of F against X, so it is equal to the gradient. And for the gradient from the graph, it is simply 4.0 minus 0 divided by 0.05 minus 0, which is simply 4 divided by 0.05. So this is 4.0 divided by 0.05. And I think that is 80. That is 80. 4 divided by 0.05, I think that is 80. Then use the figure to show that the decrease in elastic potential energy of the spring is 0.055 joules. So when the block moves from position Y to position X, from position Y where the extension is, of course we have seen position Y, the extension is 0.04, to position X where the extension is 0.1015. So let's check from the graph. 0.04 is here. So 0.04 is here. And in position Y, the extension was 0.015. 0.015 is in the middle of here. 1, 2, 3, 4, 5. 0.015 is here. So from 0.04 to 0.015, we are seeing that on the vertical axis, this is actually 1.2, and at 0.4, this is actually 3.2. This point here is 3.2 on the vertical. So we're going to simply find, because we want the decrease in elastic potential energy, we are going to find the area under this part, which is a trapezium. You can use the area of a trapezium. We call this A, the other one B, and this will be H. H will be 0.04 minus 0.015. So we are finding the energy. Decrease in elastic potential energy is equal to a half times Kx, or we can just find the area. This is a half Fx, or which is the area under the graph. Or you can use a half Kx squared, n of those. You can use a half Kx squared. So I'll just use the area under the graph, and the energy is going to be a half. We said it is a trapezium where A is 1.2, B is 3.2, that is A plus B. Then the height is from 0.4 to 0.0, sorry, it is 0.04. It is not 0.4. It is 0.04 minus 0.015. So I'll use my calculator, which is a half, that is 0.5, times brackets, I have 1.2 plus 3.2. Then I multiply this by brackets, 0.04 times 0.015. So this is giving me 1.32. How have I added this? Let me repeat again. 1.2 plus 3.2 divided by 2 times 0.04 minus 0.015. So this is 0.055. Alternatively, you could use the formula half kx squared at both points. So alternatively, you could say a half times k. Remember k we have calculated it as 80. When the extension is 0.04 at y, it will be 0.04 but squared. Then you subtract. At x, the extension was 0.015, so it is a half times 80 times 0.015 squared, and still you will get 0.055 in joules. You can still verify that. The block has a mass of 0.122 kilograms. Calculate the increase in gravitational potential energy of the block for its movement from position y to position x. From position y to position x. So we know that the increase in gravitational potential energy is equal to mg times the increase in the height h. So they have given us the mass as 0.122 kilograms. G is 9.81 times h. Let's check the value of h. It is from from position y. Position y, the distance is 0.1. To position x, the distance is 0.095. So we want the difference in height, which we shall just subtract. So this is going to be from 0.120 minus 0.095, which is going to give us 0.122 times 9.81 times open brackets 0.12 minus 0.095, close the bracket. So I'm getting 0.0299, 0.0299, which is approximately 0.030. To two significant figures, it is going to be 0.030. To two significant figures, these were three. Use the decrease in elastic potential energy stated in B and your answer in C to determine for the block as it moves through position X its kinetic energy. So this one is the increase in gravitational potential energy, yet in B we are having the decrease in elastic potential energy. We see that the decrease in elastic potential energy is not the same as the increase in potential energy. We are seeing that the decrease in elastic potential energy is not the same as the increase in gravitational potential energy. That means the other part can be accounted for by the kinetic energy. So the kinetic energy is just going to be the difference. So the kinetic energy EK is going to be equal to 0.055 minus 0.030. 0.055 minus 0.030, which is 0.025. So here it is going to be 0.025 as the kinetic energy. Then its speed. Since we already now have the kinetic energy, we can find the speed. So kinetic energy is equal to a half m v squared. So this is going to be 0.025. We make v the subject. So v is going to be the square root of 2 times 0.025 divided by the mass. The mass was given as, I think, 0.122. 0.122. So we check with our calculator. Square root of 2 times 0.025 divided by 0.122. So that is 0.64. A ball X moves along a horizontal frictionless surface and collides with another ball Y as illustrated here. So we can see some resolving. We can see if I prolong this one further, I think this angle is going to be 60 degrees. If I prolong this one further, this angle is also going to be 60 degrees. So this is going to be 0. Actually, the velocity here is going to be 6.0. To the horizontal, it is going to be cos. To the vertical, it is going to be sine. To the horizontal, it will be cos 60. To the vertical, it is going to be sine 60. So this is going to be Vx in that direction. Let's see the questions. Remember, this is not to scale. Ball X has a mass of 0.3 and initial velocity Vx at an angle of 60 degrees to line AB. Ball Y has 0.2, velocity 6 at an angle of 60 to line AB. The balls stick together during the collision and then travel along line AB as illustrated. Calculate the three significant figures, the component of the initial momentum of ball Y, that is perpendicular to line AB. The component of ball Y, initial momentum of ball Y, that is perpendicular to line AB. So we are going to resolve this velocity to 90 degrees and to be 6 sine of 60. Then we shall multiply by the mass to find the momentum. So momentum is mass times velocity. So this is going to be 0.2, which was the mass, 0.2 kilograms, times the speed, which is 6.0 sine of 60. We resolve vertically. Alternatively, you would have used the angle, which is 30 degrees to the vertical. Somebody would calculate this angle as 30 degrees, so this person resolves as 6 cos of 30. It is the same thing. So another person would consider resolving vertically and will get another alternative would be 0.2 times 6.0 cos of 30. And that would give us the same answer. So 0.2 times 6 sine of 60. And that is 1.04. By considering the component of the initial momentum of each ball perpendicular to the line AB, each ball perpendicular to the line AB, calculate three significant figures Vx. So we are resolving vertically again. Let's resolve Vx vertically again. Vertically again, Vx will point downwards and to be Vx sine of 60. It will again be Vx sine 60. And the momentum downwards will be the mass 0.3 times Vx sine 60 downwards. By conservation of momentum in the vertical should be equal to the momentum upwards. The momentum upwards is the one we have got in part A. In part A, Roman 1. So we shall say the momentum downwards is going to be 0.3, that is the mass of ball X, times this speed, which is Vx, but it is sine of 60 downwards, should be equal to the momentum upwards, which we have got as 1.04. So just press our calculator to get Vx as 1.04 divided by 0.3 sine of 60. So 1.04 divided by 0.3 sine of 60. and that is 4.00 to 3 significant figures, that is 4.00. Show that the speed of the two balls after collision is 2.4 meters per second. Now we are going to use momentum in the horizontal because after collision, they are actually in the horizontal. The first part is more of dynamics. After collision, they are in the horizontal. Part A is more of dynamics. So we resolve V in the horizontal to be 6 cos of 60. Resolving Vx in the horizontal will also be Vx cos of 60. When we sum the momentum in the x initially should be equal to total momentum after. Here they will sum up 0.2 plus 0.3 will be the total mass times the common velocity v, that is the total momentum after. So total momentum in the x before collision is 0.3 times its velocity, which we have got as 4 cos 4.0 cos of 60 degrees plus for that was for ball X. For ball Y, its mass is 0.2 times its speed, which we initially knew as 6.0 cos of 60 degrees. This should give us the total momentum after collision, which is total mass is 0.3 plus 0.2 since they stick together, times the common velocity v. So we are just going to sum up this. So I will say 0.3 times 4 cos of 60. Since this is identical to that, this is identical to the first part. I'll just multiply that by 2. So that gives me 1.2 on the left hand side equals to 0.5 V, which means V is 1.2 divided by 0.5, which is actually 2.4 meters per second. The two balls continue moving together along the horizontal friction surface towards a spring as illustrated in the figure here. So the balls are now continuing moving together with their total mass, which has been summed with a speed of 2.4. So it means they have kinetic energy here, which is a half mv squared. That is, the energy they have here is a half mv squared, where v is 2.4 before they reach the spring. The balls hit the spring and remain stuck together as they decelerate to rest. All the kinetic energy of the balls is converted to elastic potential energy. The energy stored in the spring is given by that. So all the kinetic energy is becoming elastic potential energy. The spring obeys Hooke's law and has a spring constant of 72 newtons per meter. Determine the maximum compression of the spring caused by the two balls. So the loss in kinetic energy is going to be equal to the gain in the elastic potential energy. That is a half m v squared is going to be equal to a half k x squared. So the a half was cancelled. The mass was 0.500 times the speed they had was 2.4 squared equals to the spring constant is 72 times x squared. So we just find x. So I have 0.5 times 2.4 squared. Then I divide this by 72. Then I find the square root of the answer. And that is 1 over 5, I think, is 0.2. So x is equal to 0.2 meters. It is exactly 0.2 meters. On the figure 4.4, sketch graphs to show the variation with compression x of the spring from 0 to maximum compression of part A. The magnitude of the deceleration A of the balls. the magnitude of the deceleration A of the balls. Of course, as the compression increases, it means the elastic potential energy is increasing. The kinetic energy decreases. That means the speed decreases. And if the speed decreases, it means the deceleration is actually decreasing. However, so the deceleration decreases, and if the deceleration decreases, it means that this is actually going to be a straight line, since we know that force is equal to mass times acceleration. Of course, the extension is there's a compression, and therefore kx is equal to mn. The compression is actually decreasing. Okay, the compression is actually increasing, meaning that the deceleration is also going to be increasing. And these are directly proportional, so this is going to be a straight line. So this is going to be a perfect straight line because the compression is directly proportional to the deceleration. The more the spring is compressed, the more the balls decelerate to rest. So that is going to be a straight line. Then part 2, the kinetic energy Ek of the balls. We see that kinetic energy Ek is equal to a half kx squared, and we see that as the compression increases, the kinetic energy is going to be actually decreasing more rapidly. This was potential energy. The elastic potential energy is a half kx squared, which is actually equal to a half mv squared. So because the kinetic energy is going to decrease as the elastic potential energy increases, it means as the compression increases, the kinetic energy must be decreasing because the kinetic energy is becoming the elastic potential energy. However, we notice that actually this x is squared, meaning that the kinetic energy decreases more rapidly as x increases. That means this is not going to be a straight line, but it's going to be a graph, which is going to be somehow like that. So this is going to be a graph which is going to be like this. In other words, the line has an increasing downward slope. So the line has an increasing downward slope. That is, as x increases, then the kinetic energy decreases rapidly. And of course, there is a limit. There is a limit. That's why the line must touch the x-axis, because there is a maximum compression where the kinetic energy now becomes zero. That is when now the balls come to rest. A spring is extended by a force. The variation with the extension x of the force is shown in the figure down here. So we have force against extension. State the name of the law that relates the force to the extension. Of course, this is Hooke's law. This is going to be Hooke's law. Then determine the spring constant in newtons per meter of the spring. So from Hooke's law, force is equal to kx. So the spring constant k is equal to f over x, or you can use the gradient. So this can also be the gradient. Therefore, we can now simply substitute from the graph. And I think this is 1, 2, 3, 4, 5. I think this is 7 against 5.0. So I'll just simply say 7.0 minus 0 divided by, this is 5, because this is times 10 power negative 2. So I say 5.0 minus 0 times 10 power negative 2. So I'll just press my calculator. 7 divided by 5 exponent negative 2, and that is 140. The strain energy, which is the elastic potential energy in the spring when the extension is 4.0 centimeters. We know that elastic potential energy can be a half Fx, it can be a half Kx squared, or it can be simply the area under the graph. Area under the graph. So let's look for 4.0 centimeters. So 4.0 centimeters is around here, and we want this area here to be the elastic potential energy. So the base is 4 and the height is, what is the height? So this height is 4, no, it is 5 point. On the vertical, the scale is 2 divided by 10, which is 0.2. 4 point, this is 1, 2, 3, 4, 5, that is 5.2, 0.4.6, that is 5.6. So the energy is going to be a half times 5.6 on the vertical, then times the extension, which is 4.0 times 10 power negative 2. And this is going to give us 0.5 times 5.6 times 4 exponent negative 2, which is giving me 0.112, 0.112 or 0.11 in joules. So that is 0.11. One end of the spring is attached to a fixed point. A cylinder that is submerged in a liquid is now suspended from the other end of the spring, as shown in the figure. So this is what we have. So we have the cylinder has cross-sectional area 1.2 times 10 power negative 3. The cylinder has length of 5.8 centimeters. The cylinder has weight of 6.2 newtons. Okay, the cylinder has length of 5.8, cross-sectional area 1.2, exponent negative 3, and weight 6.2. The cylinder is in equilibrium when the extension is 4.0 centimeters. Show that the upthrust acting on the cylinder is 0.6. What is upthrust? Just take you back. Upthrust, the origin of upthrust is difference in pressure between the top and the bottom of the object. So let's say the height from the top of the surface of the liquid to the bottom is h2, and the height from the surface of the liquid to the top of the object is h1. So the pressure at the bottom, I'll call it P2, is equal to h2 times density times g. Pressure at the top of the liquid is equal to h1 times density times g. And remember, pressure is force over area. So this will be F1 over A. This is F2, the area is the same. So we now have that F2 is equal to pressure P1 times area. It is P1 times the area, which is H1. This is what? This is F1. This is F1 is P1A times, this is H1 density times G times A. Then F2 is going to be equal to P2 area, which is H2 times density times G times the area. So the upthrust force, which I'm going to call Fu or F up, is going to be F2 minus F1, which is equal to the change in pressure times the area. It is change in pressure times the area, which is actually equaling to which is actually going to be equal to H2 minus H1. I'm subtracting the two equations times density times G times A, which is actually change in pressure times the cross-section area, if you want to put it like that. Or change in H times density times G times area. So we know what we mean by upthrust. However, the weight of the object is acting downwards, and that is 6.2 newtons. The weight of the object is acting downwards, that is 6.2 newtons. Let's find the tension or the force acting upwards, or the tension upwards. So we are finding the tension or the force due to the spring. The force due to the spring, which is going to be the tension, which is given by Hooke's law K times the extension E. And this is going to be K, which K is, what is K? We got K as, I think K was 140. K was 140, and the extension is 4 centimeters. So K is 140 times 4 times 10 power negative 2, which is equal to 140 times 4 exponent negative 2, and that is 5.6 newtons. That is the force due to the spring upwards, but the weight is downwards. So the upthrust is going to be, remember the upthrust also acts upwards. So the force due to the upthrust, I'm calling it F up, plus the force due to the spring, which is 5.6, should be equal to the weight downwards, which is 6.4. I mean 6.2 if there is equilibrium. So this is going to be 6.2. That means if we subtract to get the force up, the force upwards is going to be 6.2 minus 5.6, which is going to give us, you can check this on your calculator. So that is 6.2 minus 5.6, which gives you 0.6 as required in newtons. Then calculate the difference in pressure between the bottom face and the top face of the cylinder. Difference in pressure. So I have showed you that the difference in pressure actually can be got from these two expressions. You subtract, you look at those two expressions. Pressure at the top can be given as that. I mean at the bottom, pressure at the top can be given as that. Then we can find a difference. So pressure at the top, I'm going to call it H1 density times G. Pressure at the bottom is going to be H2 density times G. Then difference in pressure is going to be H2 minus H1 times density times G. But note that H2 minus H1 is just the height of the cylinder. H2 minus H1 is just the height of the cylinder, which is 5.8 centimeters. Therefore, the pressure, the change in pressure could be that. But also, we have seen that the difference in the force, the upthrust force F up was the change in pressure times the area. So it means we can also say the change in pressure is going to be equal to the force, the upthrust force, divided by the area, which is going to be 0.6 divided by the area, which was 1.2 times 10 power negative 3. And this is going to give us 0.6 divided by 1.2 exponent negative 3, which gives us 500. So that is 500. But we can use the same formula, this formula here, because this is difference in the height of the bottom and the top, density times G, that is change in pressure. So we shall use this in our next part. Calculate the density of the liquid. Calculate the density of the liquid. So we have seen that change in pressure is equal to now H2 minus H1 is change in the value of H times density times G. And this change is actually equaling to 500. So it means the density is going to be equal to 500 divided by the pressure is 500 divided by the change in H, which is 5.8 times 10 power negative 2. Then we multiply this by G, which is 9.81. So we press our calculator again. So we have 500 divided by, let me begin by dividing by 9.81, and I continue dividing by 5.8 exponent negative 2, whichever way you divide. So that is giving me 879.77. 879.77. 800 not 78. 878.77, which is approximately 880. 880. Okay, so note the basics about pressure. Note the basics about pressure. We have seen how the upthrust force is the difference in the two forces, and it was the difference in the pressure times area. And it is also, when you use the values, the density H and G, you notice that it will be H2 minus H1 times density times G times area. So you need to note that those relations. We shall see that again in force, density, and pressure. We were interested on the other in the other part of deformation, which is part D maybe. The liquid in C is replaced by another liquid of greater density. State the effect, if any, of this change on the upthrust. We have seen that upthrust force is equal to the change in pressure or difference in pressure times area. The liquid in C is replaced by another liquid of greater density, and this is equal to a change in pressure is change in value of H times density times G times area. So even if H is not changing, G is not changing, A is not changing, but this is of greater density, we notice that upthrust force increases. So this one increases. Then state the effect, if any, of this change on the extension. What happens to the extension? Note that the upthrust force, the force upthrust was equal to actually the weight downwards minus the tension upwards, which was the weight, the tension was K times the extension X. So we are saying state the effect, if any, of this change on the extension of the spring. The liquid is replaced by another liquid of greater density. So it means the upthrust force has increased. So F up has increased, but W has stayed the same. So you notice that actually T or Kx, so Kx is going to be F up. Kx is going to be actually the weight minus F up. Just want to show you how it behaves. Kx, I'm making Kx the subject, is going to be the weight minus force due to the upthrust. When this part becomes greater because the density has increased, it means since K is a constant and the weight is constant, it means this quantity here is becoming smaller. And if this quantity is becoming smaller, you divide by K, it means x is going to be smaller. So it means this one decreases. That one decreases. So I think the analysis is clear. I don't know whether it is clear. I can try to repeat it here again. So here the tension is going to be equal to the weight minus the upthrust, which I'm calling F up. But the tension is Kx, or the force in the spring is Kx, which is equal to the weight minus the upthrust divided by K divided by K. It means the X tension is equal to the weight minus the upthrust force divided by K. K is a constant, is not changing. Weight is not changing. The upthrust is becoming bigger. It means the difference between weight and upthrust becomes smaller when the upthrust is bigger. Then divide by K. It means X becomes smaller. That's why I'm saying it decreases. Okay, define for a wire stress. Stress is force over cross-sectional area. Then strain. Strain is extension divided by the original length. A school experiment is performed on a metal wire to determine the Young modulus of the metal. A force is applied to one end of the wire, which is fixed at the other end. The variation of the force with the extension x of the wire is shown in the figure here. The maximum force applied to the wire is F1. The gradient of the graph line in the figure 4.1 is G. The wire has initial length L and the cross-sectional area A. Determine an expression in terms of A, G, and L for the Young modulus E of the metal. So by definition, Young modulus E is equal to stress divided by strain. Stress is force over area. Strain is extension of original length. We get the reciprocal. So it will be extension x over original length, which is given as L. No, it will be the reciprocal. We are getting the reciprocal since we are dividing. We get the reciprocal, so that will be original length L over extension x. If I try to rearrange this, this will be F over x times L over A. And we know that F change in F over change in x, that is going to be the gradient since the graph is of F against x. So it means Young modulus is going to be equal to the gradient times L over A. And the gradient is given as G. So this is going to be G L over A. So this is going to be GL divided by A. So that is going to be our Young modulus. A student repeats the experiment in B using a new wire. It is a new wire that has twice the diameter of the first wire. The initial length of the wire and the metal of the wire are unchanged. So L remains the same. The metal is the same, so it means Young modulus is the same. Draw the graph line representing the new wire for the force increasing from F1 to F equals to F1. F equals to 0 to F equals to F1. So the maximum force is the same. So the new material has the same initial length and the same Young modulus. From the expression for Young modulus as force, E equals to F or original length over area times extension, which I called X. I'll just modify this. Remember, area is equal to pi d squared over 4. That is pi r squared. They have told us that the new wire has diameter. The diameter of the new wire is twice that of the first. So I need to bring in diameter in this expression. So it means Young modulus is going to be where there is area, I'm putting pi d squared over 4. So it becomes 4f(L) divided by a times x. So let's get to equations now. For the first one, f1, I'm making f1 the subject. For the first, if I make f1 the subject, you notice that, okay, here there is pi 4fl over area, which I've replaced as pi. This is pi d squared. Pi d squared times x. I just removed the a in the first equation. So f, making f the subject, force is equal to Young modulus times pi times d squared times x divided by 4L. For the first wire, F1 was equal to E Young modulus pi d squared. The extension was, how many small squares are these? I think these are 16 squares. So I would say the extension was 16 squares. Just know this is 16 is the number of squares. Divide by 4 times L. For the second one, F1 should be equal to, Young modulus is the same, pi, the diameter is twice d, but this is squared. We don't know the number of small squares, I'll put there x. Divide by, this is still 4L. So these two equations are equal, you can equate them mathematically, this one and this one. We want to find x. So you notice that E is on both sides of the equation, pi is on both sides, 4L is on both sides. So I remain with d squared times 16 is equal to, when I square 2d squared becomes 4d squared times x. D squared has also cancelled. So it means x is going to be 16 divided by 4, which is 4 small squares. So it means for the second wire, F1 will give an extension equal to 4 small squares. So this is 1, 2, 3, 4. So that means my graph is going to be here. So the line will be there, stopping on 4 small squares. Another student repeats the original experiment in B Roman 1, increasing the force beyond F1 to a new maximum force F2. The new graph obtained is shown here. On the figure, shade an area that represents the work done to extend the wire when the force is increased from F1 to F2. Work done from F1 to F2, that is the area under this part of the graph. Then, so that is the area under that part of the graph. So we just shade that region. Then explain how the student can check that the elastic limit of the wire was not exceeded when F2 was applied. Of course, we remove the force F2 and see if the wire goes back to the original length. So I remove the force F2 and see if the wire goes back to its original length. So if a material goes back to its original length or shape, it means the elastic limit is not exceeded. Each student in the class performs the experiment in B Roman 1. The teacher describes the values of the Young modulus calculated by students as having high accuracy and low precision. High accuracy means the average of the values would give the true value or the accepted value. And low precision means the values of each student, the values of the students were widely further apart. In other words, they have a very large range. Explain what is meant by low precision. In this case, the values have a wide range. The values have a large range. The values have a large range. That is, the values, when you get the highest value minus the lowest value, the range is very large. So they are more scattered, widely scattered. A spring is fixed at one end and is compressed by applying a force to the other end. The variation of the force F acting on the spring with its compression X is shown in the figure below. A compression of 0.045 meters is produced when a force F1 acts on the spring. The spring has spring constant 800 newtons per meter. Determine F1. So F is equal to K times X, that is by Hooke's law. So it means F1 is going to be the spring constant K, which is 800, times X, which is 0.045. We check with the calculator. 800 times 0.045, and that is 36 newtons. Use the figure 3.1 to show that for a compression of 0.045 meters, the elastic potential energy is 0.81. How do we find elastic potential energy? Elastic potential energy is a half kx squared, or we can have a half times F times X, or this could be the area under the graph. So I'll just use this one or the other one for area, that is a half. And the force, we have got F1 as 36 times X, which is 0.045. And we press the calculator. By the way, you could also have used a half times K, which is 800, times X, which is 0.045 squared. So that is 0.5 times 36 times 0.045, and that gives us 0.81, exactly 0.81 in joules. A child's toy uses the spring in A to launch a ball of mass 0.2 kilograms vertically into the air. The ball is initially held against one end of the spring, which has a compression of 0.045 meters. The spring is then released to launch the ball. The kinetic energy of the ball as it leaves the toy is 0.72. As it leaves the toy is 0.02, 0.72 joules as it leaves. So that means, remember, this was the energy stored, which is stored in the compression of 0.045 meters. But the kinetic energy as it leaves is 0.75. So this is the useful energy output. This was the energy input. The toy converts elastic potential energy of the spring into kinetic energy of the ball. Use the information in A Roman 2 to calculate the percentage efficiency. So efficiency is going to be the useful output energy, useful output over the energy input. over the energy input, which is going to be 0.72 divided by 0.81 times 100. So 0.72 divided by 0.81 times 100, which is 88.8% or approximately 89%. Determine the initial momentum of the ball as it leaves the toy. Initial momentum. We have the kinetic energy as it leaves, and we know kinetic energy is a half mv squared. And they have given it to us as 0.72, which means v squared of v is going to be 2 times 0.72 divided by the mass of the ball was, the mass of the ball is 0.02. So I will divide this by 0.02 and I find the square root, that is v. But remember, momentum is mass times v. So the momentum is again going to be 0.02 times the value of v, which is the square root of 2 times 0.72 divided by 0.02. So we check with our calculator. 0.02 times the root of open brackets. So I will have 2 times 0.72, then divide by 0.02. That is 0.1697, which is approximately 0.17. So this is 0.17. The ball leaves the toy at point A and moves vertically upwards through the air. Point B is the position of the ball when it is at maximum height h above point A, as illustrated here. So we see the ball of mass 0.02 is leaving with that kinetic energy. The gravitational potential energy of the ball increases by 0.60 joules as it moves from A to B. The gravitational potential energy increases by 0.6. Calculate H. So the increase in gravitational potential energy is given by mg times the increase in the value of h, or times h. So it means the increase in the value of h, or just h, is going to be as 0.60 divided by the mass, which is 0.20 times 9.81, which is g. So 0.6 divided by 0.2 times 9.81. So that is 0.31. Is it 0.31? Let me check it again. Sorry, the mass is 0.02. Sorry about that. The mass is 0.0. The mass is 0.02. What has happened to this pen? So I will say 0.6 divided by open bracket 0.02 times 9.81. So this is giving me 3.058, which is 3.1. So the change in the value of H from A to B is 0.31, I mean 3.1. Determine the average force due to air resistance acting on the ball for its movement from A to B. From A to B. So if there is air resistance, there must be work done against air resistance. The work done against air resistance is going to be force times the distance, where the force is the air resistance. And of course, the work done is going to be the difference in the energy, which is going to be actually 0.72 minus 0.60, because the change in gravitational potential energy is 0.60, or the increase in gravitational potential energy is 0.60. Yet the kinetic energy was 0.72. That means some energy does not contribute to the increase in gravitational potential energy, and that is the difference. That energy goes into doing work against air resistance. So this will be times the force times the air resistance, times distance, which is 3.1. That means we shall just get our force F as 0.72 minus 0.6, which is 0.12 divided by 3.1. So the answer divided by 3.1, and this is 0.039. 0.039 to two significant figures. So that is the average force due to air resistance. When there is air resistance, the ball takes time t to move from A to B. Let's see when there is air resistance. This is the ball. It is moving upwards, but the forces acting are the weight downwards. Air resistance acts in the opposite direction. So this is the force due to air. Do we notice that the resultant force downwards is higher? If there is no air resistance, the ball is moving upwards, but the weight is acting downwards. The resultant force downwards is due to to the weight alone. So it means in part A, in the first case, the ball will slow down very fast because the resultant force on the ball is greater. In the second case, the ball will not slow down very fast because the resultant force on it is smaller than the first case when there was air resistance. Since, remember, the resultant force is downwards, and force is equal to mass times acceleration. If the resultant force is small, it means the acceleration or deceleration is going to be small. Therefore, a ball in the first case where there is air resistance will reach a maximum point in a very short time than a ball when there is no air resistance. So we can say the resultant force on the ball is now less. That is when there is no air resistance. The resultant force is now less than that with air resistance. If the resultant force is smaller, it also means the deceleration is smaller, so it will take more time to reach the highest point. So the time taken is more than t. The time taken is more than t. Okay. State Hooke's law. We know that for Hooke's law, extension is proportional to the force provided the limit of proportionality is not exceeded. Extension is proportional. Proportional to the force, provided limit of proportionality is not exceeded. Is not exceeded. Provided limit of proportionality is not exceeded, that is Hooke's law. A spring is fixed at one end. A compressive force F is applied to the other end. The variation of the force F with the compression X of the spring is shown here. Show that the elastic potential energy of the spring is 0.64 joules. I think this is now easy when its compression is 16. So just know that elastic potential energy or the strain energy is actually going to be equal to a half Fx, or you can use a half Kx squared. If the spring constant, of course, this will mean you have to find the spring constant, but this is essentially the area under the graph. Strictly, this area is with the axis of the extension. It is not with the axis of the force, because sometimes the graph is drawn differently. It's area under the graph. So this is going to be a half. I'll take F as 8, and I'll take the extension as 16 times 10 power negative 2 to change it from centimeters to meters, which is equal to a half is 0.5 times 8 times 16 exponent negative 2, which is 0.64. So this is 0.64 joules exactly. Okay. The spring in B is used to project a toy car along a track from point X to point Y as illustrated in the figure. We can see the figure. It is from point X to here. This is 0.3 meters. Then it now takes the path of a circular path of radius 0.12. Then it now moves this distance of 0.25. That means total distance from X to Y is going to be 0.30 plus the circumference, which is pi d, plus 0.25. That is total distance from X to Y. So the spring is initially given a compression of 16 centimeters. The car of mass 0.075 and 76 kilograms held against one end of the compressed spring. When the spring is released, it projects the car forward. The car leaves the spring at point X with kinetic energy that is equal to the initial elastic potential energy. That is a very simple, important point. The kinetic energy is equal to the initial elastic potential energy of the compression. The car follows the track around a vertical loop of radius 0.12 meters and then passes point Y. Assume that friction and air resistance are negligible. Calculate speed of the car at X. At X, of course, the elastic potential energy here becomes the kinetic energy. So the elastic potential energy is going to be considered using the elastic potential energy that we already calculated in part B, where when the compression was 16, the elastic potential energy is 0.64. So the elastic potential energy is the one which is becoming kinetic energy. So we shall say kinetic energy is equal to a half m v squared, and this is equal to the elastic potential energy, which is 0.64. So it means V is going to be the square root of, I multiply 2 by 0.64, I divide by the mass. I think the mass was, what is the mass of this car? 0.076. So this will be time over 0.076. So 2 times 0.64 divided by 0.076, square root of the answer, that is 4.1. So this is 4.1 meters per second. Calculate the kinetic energy of the car when it is at the top of the loop. At the top of the loop. First of all, let's find the change in the gravitational potential energy. So the gain in gravitational potential energy at the top is mg times h, which is going to be, of course, here I will just say change in h, which is going to be mass 0.076, g is 9.81. Then at the top, h is, what is h at the top? So since the radius is 0.12, the top is at a distance of 0.24 meters. So height is going to be 0.24 meters. So at the top, that will be times 0.24. And this is going to be 0.076 times 9.81 times 0.24. So that is 0.18. 0.18 joules. That is the gain in gravitational potential energy. But remember, the car at x had kinetic energy which was 0.64, but it has gained potential energy of 0.18. It means it is still having a kinetic energy. So the kinetic energy, it has both potential energy and kinetic energy. The kinetic energy there, since part of the 0.6 has become potential energy, then it means the kinetic energy remaining is going to be 0.64 minus 0.18. 0.64 minus 0.18, and that is 0.46. So what remains as kinetic energy is 0.46. So that is 0.46 joules remains as kinetic energy. Then the speed of the car at y, since air resistance is negligible and air resistance is negligible and frictional forces are also negligible, then it means the loss in kinetic energy when it is going up must be equal to the gain. The loss in kinetic energy must be equal to the gain in potential energy, which we have seen as 0.18. Now, when it is falling, it will again lose the gravitational potential energy and gain back its kinetic energy. So it means at point y, it will have the same kinetic energy as it was at point x. That means its speed will remain the same as that at point x. So since air resistance and friction are negligible, the speed at y and at x are going to be the same. So that is 4.1. In practice, resistive force due to friction and air resistance, acts on the car so that its kinetic energy at y is 0.23 instead of 0.64. Oh, sorry, it is 0.23 joules less than its kinetic energy at x. At x, remember, it was 0.64. At y, it is 0.23 less than, so it is 0.64 minus 0.23. So this is the change in kinetic energy. Determine the average resistive force acting on the car for its movement from x to y. So the work done against resistive force is going to be 0.23 because the difference in kinetic energy is 0.23 joules. But work done is equal to force times the distance, total distance. Force times the total distance. Let's find the total distance. The distance between x and y is equal to 0.30 plus the circumference of the circle, which is pi d, plus 0. Let me see, 0.30 plus the circumference of the circle plus 0.25. So circumference of the circle, I think it is pi d. The diameter is twice the radius, so plus 0.25. So this is 0.30 plus pi times diameter, which is 2 times 0.12, that is the radius, plus 0.25. So we check the calculator, 0.3 plus 0.25 plus, open brackets, I'll say pi times 2 times 0.12. So here I'm getting the distance as 1.3 in meters. 1 point, sorry. The distance is 1.3 in meters. So I want the distance, I mean the force. So the force F is going to be 0.23 divided by 1.3. So 0.23 divided by 1.3, that is equal to 0.176, which is approximately 0.18. So if the air resistance and resistive forces are not ignored, then total distance is going to be the distance 0.3 plus the circumference of the circle plus 0.25. Then our work done is force times distance. So we just divide and find the force. Okay. A uniform metal bar initially unstretched has sides of length W, X, and Y, as shown in the figure. The bar is now stretched by a tensile force. See where the tensile force is acting. It means W is the one which changes to Z. And Y is not changing much, X is not changing much. The changes in the length X and Y are negligible. The bar now has sides of length X, Y, and Z, as shown here. Determine expressions in terms of sum or all of F, W, X, Y, and Z for stress. Stress is equal to force over area. The force is still F. The cross-sectional area is X times Y. So this is F over XY. Then the strain. Strain is extension over original length. Extension, the original length was W minus the new length is Z over original length, which is actually, so the new length is Z, it is Z minus W. So the new length is Z minus the original length, which is W, over the original length, which is W. So this is Z minus W over W. Okay, the Young modulus. We know Young modulus, E is equal to stress, which is force over area, divide by, I get the reciprocal original length over extension. So the force is F, the area is XY, original length was W, and the extension is Z minus W. So this is going to be F W divided by xy into z minus w. So that is the Young modulus. A copper wire is stretched by a tensile force that gradually increases from 0 to 80 newtons. And with extension of the tensile force, the variation with extension of the tensile force is shown in the figure. So we have force against extension. State the maximum extension of the wire for which it obeys Hooke's law. So just look for where the straight line stops on the graph, and I think it is it's around here. It is between 2 and around 2.4. So I'll just take one that is 2.2. The scale on the x-axis is 2 divided by 10, that is 0.2. So here it is 2.2 if the straight line stops approximately there. Or maybe you could be seeing 2.4. Yeah, but it's actually 2.2 in millimeters. Then use the figure to determine the strain energy. Strain energy is the elastic potential energy, and energy is equal to a half times F times X, which is a half kx squared, which is actually the area under the graph. The area under the graph, so this is a half. We want the force of 120, so I'll just say times 120. Let's see the extension corresponding to 120 newtons. So 120, this is 80. The scale on the vertical is 80 divided by 10, which is 8. Each small square is 8. So this is 88, that is 96. This is 104. This is 110. And this is 118. And let me see. 120 minus 80 divided by 8. Let me just use that simple method. 120 minus 80 divided by 8. That is 8 small squares. So to reach 120, I'll add 8. 1, 2, 3, 4, 5, 6, 7, 8. That is 120. So 120 is corresponding to this time. So this is in the middle of the box here. On the x-axis, each small square is 0.2, so half a box is 0.1. And these are 1, 2, 3, 4, 5, 6, 7, 8 and a half. 8.5 times 0.2, that is it 1.7? Let me check. 120 minus 80 divided by the scale, which was 8. We got 5. No, it is not 8 small boxes, it is 5. 120 is 5 small boxes. 120 minus 80 divided by 8, it is 5. So I count 5 small boxes again, sorry for that. 1, 2, 3, 4, 5. And it is here on the x-axis. On the x-axis, it is here, which is 1, 2, 3, 4, 5, 6, 7. So I have 7 times the scale, 0.2, that is 1.4. So x is 1.4, so this is times 1.4 times 10 power negative 3, since it was in millimeters. So I'll check this with my calculator. 120 times 1.4 exponent -3 divide by 2, so that is 0.84. 0.84, no, 0.084. It is 0.084. Explain why the work done in stretching the the wire to an extension of 12 millimeters is not equal to the energy recovered when the tensile force is removed. We are seeing from the graph that the material entered its plastic region. So when you extend beyond around 2.2, it means when the deforming force is removed, the material will not go back to its original length. Therefore, some work is wasted or becomes internal energy, or some energy is dissipated as thermal energy in the process because the wire goes into the plastic region. This is plastic. It goes beyond the elastic region. So we simply say the wire goes past the elastic limit, or you can say it enters the plastic region. The wire enters the plastic region, so some energy is dissipated. Some energy is dissipated as thermal energy, or it becomes internal energy. Some energy becomes internal energy, so the temperature of the wire may increase. So some energy becomes internal energy. That is, the temperature of the wire is most likely going to increase because the total kinetic energy of the molecules will increase. Okay. A child moves down a long slide as shown in the figure there. The child moves from rest at the top and X of the slide. An average resistive force, 76 newtons, opposes the motion of the child as they move to the lower end Y of the slide. The kinetic energy of the child at Y is 300 joules. The decrease in gravitational potential energy of the child as it moves from X to Y is 200. Determine the ratio kinetic energy at Y when the resistive force is 76 newtons over kinetic energy of the child at Y if there is no resistive force. We see the decrease in gravitational potential energy as this, and the decrease in gravitational potential energy if there was no resistive force would be equal to the kinetic energy, but now they are not equal. So it means this ratio is going to be simply, when there is a resistive force, the kinetic energy is 300 joules. If there was no resistive force, the kinetic energy would be equal to the decrease in gravitational potential energy. So that means this will be over 3,200 joules. So this will be 300 divided by 3,200, and that is 0.94. Okay. Use the answer in A to calculate the ratio speed of the child at Y when the resistive force is 76 newtons over speed of the child at Y if there is no resistive force. So we know that speed will be got from the expression for kinetic energy. Ek is equal to a half mv squared. And we know that V is going to be twice the kinetic energy divided by the mass. And I'll just get the speed at y when the ratio, so the first speed, or let me say the ratio, this is by the 1 under the square, the ratio will be equal to the square root of twice the kinetic energy over the mass when there is the speed at y when the resistive force is 76. This is going to be when there is resistive divided by again 2ek over m when there is no resistive force. So note that the 2 is going to be constant, it cancels, the mass is the same, it cancels. So this is simply going to be equal to the square root of the ratio of kinetic energy when there is a resistive force over the ratio of the kinetic energy when there is no resistive force, which is going to be the root of 300 divided by 3200, which is the same as the square root of 0. Is it 0.09? So this is 0.094. So I get the square root of the answer, that is 0.31. So this is 0. Is it 31 or 0? 0.31. Yes. So the ratio there is going to be 0.31. So I consider the ratio when the speed when there is a resistive force over the speed when there is no resistive force. I just made the square root of expression for kinetic energy when I made V the subject. Because 2 is a constant for both, whether there is a resistive force or not, the mass is the same. It is only the kinetic energy Ek which remains. So M cancelled, M cancelled, you remain with Ek for resistive, Ek with no resistive force. And that gives you 0.31. Calculate the length of the slide from X to Y. We have the resistive force is 76 newtons. The work done, the energy lost when doing work, it must be 3,200 minus 300 because not all the loss in gravitational potential energy has become kinetic energy. So work done is force times distance. The work done against friction force is going to be equal to 3,200 minus 300, which I think this is 2,900 joules. That's the work done against friction. But we know that work done is going to be equal to the frictional force times distance. So this means 2,900 is going to be equal to the frictional force, which is given as 76, times the distance, which is going to be now the length. So the length is going to be 2,900 divided by 76, which is 38.15 or approximately 38. So this is 38 meters. At end Y of the slide, the child is brought to rest by a board, as shown in the figure. A spring connects the board to a fixed point. The spring obeys Hooke's law and has a spring constant of 63 newtons per meter. The child hits the board so that it moves to the right and compresses the spring. The speed of the child becomes 0 when the elastic potential energy of the spring has increased to its maximum value of 140 joules. The elastic potential energy has increased to its maximum value of 140 joules. Calculate the maximum compression of the spring. So We know that elastic potential energy is a half kx squared, and the maximum is 140. So this will be a half. The spring constant is 63, then x squared. So we find x squared. We find x. So x is going to be the square root of 2 times 140 divided by 63. So it is 2 times 140 divided by 63 square root of the answer, which is 2.1. So the maximum compression is 2.1 meters. Calculate the percentage efficiency of the transfer of the kinetic energy of the child to the elastic potential energy of the spring. So the elastic potential energy is 140, but the energy with which the child reaches the board is actually 300 joules, because the kinetic energy of the child at y is 300 joules. That is the input energy. But the elastic potential energy is 140. So the efficiency is going to be the useful energy output over the energy input. So efficiency is equal to the energy output over the energy input, and we shall multiply this by 100 to get it as a percentage. So what is converted into elastic potential energy is just 140, but at y the child has energy as 300 where he hits the board. So this is times 100. So we have 140 divided by 300 times 100, which is 46.6 recurring, which is actually 47%. The maximum compression of the spring is x naught. Sketch a graph to show the variation of the elastic potential energy of the spring with its compression x from x equals to 0 to x equals to x naught. So elastic potential energy is a half k x naught squared. So elastic potential energy increases as x naught increases. It is maximum when x naught is maximum. Therefore, it should touch the x naught, the vertical line showing x naught. However, you notice that E increases more rapidly than x as x naught increases, because we see E is directly proportional to x naught squared. That means this graph is going to be a curve with an increasing gradient. So this is going to be a curve with an increasing gradient because E increases more rapidly as x increases. So it will be a graph with increasing gradient touching. It should be touching the x naught because there is a maximum value there. Let me try to increase the weight. The graph should be touching the point of x naught. So I am saying that this graph, the curved line from the, of course, when there is no compression, there is no elastic potential energy. That's why the graph starts from 0, 0. But the curved line must have a gradient. The gradient of the line increases. It can't be a straight line, yet x naught is squared. Yet x is squared, so it can't be a straight line. And lastly, for dynamics, there will be no any other part of the video. This is the only video for dynamics. The last question for dynamics, deformation of solids, not dynamics. Sorry for that, I think I'm tired. Lastly, for deformation of solids, there will be no part 2. I made this long enough. A spring is suspended from a fixed point at one end and a vertical force is applied to the other end as shown in the figure here. The variation of the applied force F with the length L of the spring is shown in the diagram. So we have F against L. We can tell the extension here as 60 minus 20, and the force here, maximum force here is 30. Determine the spring constant K. So the spring constant can be the change in the force over the change in the length L, or the extension, which can be actually the gradient. So this will be 30 minus 0 divided by 60 minus 20, but in the denominator it was in centimeters, so it is times 10 power negative 2. So that is 30 divided by 60 minus 20, I think that is 40, so I'll just simply say 40 exponent negative 2, and that is 75. So K is 75. Then determine the elastic potential energy in the spring when the applied force F is 15 newtons. The elastic potential energy is equal to the area under the graph. Area under the graph, which can be the same as a half kx squared. You can use kx squared if you have k, which is the same as a half fx. I'll just use a half fx because it is still area. So this is a half, and f is going to be 15. X was from 60 to 20, which is 15. Let me see, 15 newtons. 15 newtons, I think it is the center. 1, 2, 3, 4, 5. That is 15. And this is going to be 40 minus 20. That is 20. 40 minus 20, which is 20. So the extension here is 20 times 10 power negative 2. Or you could use a half kx squared, which will be a half times k, which is 75, times x, which is 20, times 10 power negative 2, but this should be squared. So this is going to give us the same values. So I will just say 0.5 for a half times 15 times 20 exponent negative 2. And that is 1.5. So the elastic potential energy is 1.5 joules. That marks the end of the deformation of solids. That marks the end of the formation of solids. See you in another episode of Learning Physics with me. I wish you all the best, and bye bye.